Here we go. Okay, so thank you all for coming. Every year, I begin this meeting with I guess, a forgettable speech. So this year, I've prepared another forgettable speech to open the meeting, and then we can start with the talks. So every so often, I'm asked to write a short summary explaining what the Global Meteor Network is, either for a methodology section in a scientific paper or an abstract for a talk. And I usually write that it is a worldwide network consisting of more than 1,000 cameras in 45 countries and more. But I feel that this technical description doesn't really capture the essence of the GMN. Putting the numbers and technical details aside, the first word I would choose to describe the GMN is community. Perhaps the best way to see what we achieved is the fact that before we formed the GMN, I knew very few of you who are here today. And so many of you who are deeply involved in the network have now spent your time on other hobbies before you joined. I want you to ask yourself 5 years ago, what did you do in your free time that involved thinking about meteors, or at least as much as today? And I feel that the greatest achievement of this project is just that you are now actively thinking about science and how you can contribute, helping to uncover mysteries of our solar system. And sometimes I ask myself, how did this happen? And it almost feels like we somehow tricked you into thinking about meteors. But I hope that this focused interest, this fire of curiosity never stops burning inside of you. So we still have a lot of work to do. And in fact, in meteor science, the job will never be done. There's always going to be an unknown meteor shower outburst. There's always going to be an interesting fireball, which will take up all of our time and potentially lead to groundbreaking discoveries. The GEMIN started as a radical experiment. Our work is privately funded, but we make all the data products public. And our guiding principle is borrowed from the free software movement, where software is both free as in free speech, but also as in free beer. Is this naive? Perhaps. This freedom provides many benefits, though. And let's say if I was to abandon the project or become out of touch, as it happens in academia, the community can completely take over and set up an alternative version of the project. And this constraints keep me accountable and active as a coordinator of the project. The GMN is also a radical experiment in diplomacy. Regional networks, who are not in good terms, still contribute to the GMN regardless. And this sharp focus on forming a central forum for the exchange of ideas and data takes priority and directly informs our design decisions. For example, I found that collaboration is smooth sailing for meteor showers and fainter meteors in general. However, when it comes to meteorite dropping fireballs, things take a sharp turn and issues immediately arise. And this is why there's much less central integration when it comes to fireballs, and things are largely left to regional coordinators to manage. And this is so that we never compromise the integrity of the global network. But the data that is public, for the first time, there's so much data that there's so many things to do with it that we don't have to keep the data closed. But in fact, are actively looking for people to analyze it. And this is going to be the general theme of the meeting today. I invited several speakers who will tell us how they're using GMN data and methods in their research, both in meteor science and beyond. And I hope that this is just the beginning of our work having impact across scientific fields, which is only possible through our dedication to open source software, open data, open documentation, and community building. These I see as our core values, which are removing barriers and red tape around knowledge transfer for the benefit of all. And finally, I would personally like to thank all of you who contributed to the network, either with funds, time, or simply goodwill. I hope you will stick around for many years to come, and I declare the meeting open. And as we usually do, very shortly in the beginning, we have a few minutes of introductions, and we'll continue having introductions later on. We just have 5 minutes, so the way I see this is you raise your hand in Zoom, and then I will call your name, unmute yourself, just very quickly say, oh, I'm this person from here, and just a very one short sentence of what you do. So I'm going to start. I'm Dennis. I'm a postdoc at Western University in Ontario in Canada, and I like meteors. So please raise your hand, and I'm going to quickly introduce you, and I'm going to call you up as you come on my screen. So Paul Rogemans, go ahead.
Hello, I am Paul Rogemans from Belgium. I am about 50 years now active with Meteor work, and I will give some presentation in a few minutes. Thank you.
Thank you, Paul. Tim Cooper, go ahead.
Hi, I'm Tim Cooper from South Africa. I'm involved with the GMN Outreach Project together with Radim, and we're busy looking at installing cameras at secondary schools.
Thank you, Tim. Mark Sufeski.
Hi, I'm Mark. I'm in Indiana, United States. My station's been on the air about a year. I'm pretty much a beginner, hoping to learn more.
Thank you, Mark. Bill Cook, go ahead.
Hi, I'm Bill Cook. I'm lead for NASA's Meteoroid Environment Office, so do meteors for a living.
Thank you, Bill. Mike.
Hi there, I'm Mike Mazur. I'm at Western with Dennis in the meteor physics group, and well, like all things meteors, and now it's transitioned into satellites.
Thank you, Mike. Any more takers? Come on, we have a few more minutes to fill. We have Bense, go ahead.
Hi everyone, my name is Ben Seguchik. I'm just an amateur. My profession is biology, so it doesn't have much to do with fireballs and meteors. Currently, I'm using the WMPL software, which is developed by you, Dennis. So that's why I'm here. I will also take or give a short presentation about recovering the Riebeck meteorite.
Thank you.
Thank you.
Next up, we have Dave Jones.
Hi there, Dennis and everyone. I'm Dave Jones. I'm an amateur in all of this, but I've been doing meteor detection for about 13, 14 years. And I've built about 120 of the UK cameras. So it's my fault you've got so much data. Apologies for that.
No worries. Thank you. Simon Sanders, go ahead.
Hi, everybody. I'm in the UK too. I've been running my camera in the UK bit of the GMN for almost exactly a year now. And hoping to get into a bit of radio work as well over the coming months.
Oh, that's very cool. Thank you. James Shepherd, go ahead.
Hi, I'm Jamie Shepherd from Scotland. I'm in the Highlands of Scotland. I've been sticking fisheye lenses up on the roof since I was a teenager, but I joined GMN in 2022 and I now operate 3 cameras, and I'm absolutely mad about analyzing data.
Amazing, thank you. We have a few more minutes to fill, so I want to see those hands up. Someone who this is their first time, or someone who's this is their 4th time at the meeting. So Howard, go ahead.
Hi, my name is Howard Eden. I run camera US002J here in the center of the United States. I've been interested in meteors for a couple decades now. I'm really happy to participate in this program, and I'm great you put it together, Dennis.
Thank you, Howard. Pete Ashman, go ahead.
Yeah, I'm Pete Ashman. I'm in Albuquerque, New Mexico. I manage the New Mexico Meteor Array. Got started with GMN in 2018, actually. So I'm an amateur, retired for many years now, but it seems that all my spare time is taken up with meteor cameras and managing our local network. Thanks.
Awesome. Thanks so much, Pete. And then let's have one more, and then let's start with Paul Stock. So we need another taker. Roel, go ahead.
Yeah, Roel Gaardmans here from the Dutch werkgroep Meteor. I'm here with my son, who is aspiring to be a member of the same working group. We have one GMN camera on the roof since almost a year now. And in real life, I'm a director of cybersecurity.
Awesome. Thank you. And I think our time is up. We will continue introductions later on. And now it's time for Paul Rogermans to tell us about the status of the network in the past year. So Paul, go ahead.
Okay. Okay. To look at the summary of the 2023 achievements of the Global Meteor Network, we look at it from an historic perspective. These are the points I want to discuss in this talk. So let's start with the historical perspective. In fact, meteors was something poorly known in the past. We have to go until into the 17th century when Edmund Halley was, according to what I could find, the very first one to mention that they were from cosmic origin. Before, it was believed that meteors were just something like thunderstorm or lightning, aurora. They had no idea what it really was. And we have to go to the 18th century, end 18th century, with Ernst Gladney, who published a book suggesting that the meteors were something coming from space. The very first double station meteor observations took place end 18th century in 1798, when two students, Brandes and Benzenberg, at Göttingen University, went at two different sites to plot visually meteors and try to calculate the position in the atmosphere. That was the very first multi-station observation ever done. But their work remained totally unknown, and with the Leonid return in the 1799, people still didn't know what meteors actually were. Nature came to help with about 3,000 meteorites that dropped in 1803 in a small town in France, and this was investigated and considered as a proof meteorites were coming from space. But still, this was a very small circle of people. Publication was no internet in that time. Even publications, letters to be sent, post stamp had to be invented still. Most people didn't know at all about all these discoveries. We have to go a little bit further in the 19th century, about 1830 or 1840, when Adolf Kettler started to collect data about meteors. He was the first, after about 40 years without any attempts, to organize again multi-station meteor observations in Belgium, done from Brussels, Ghent, Liège, and they calculated trajectories. He also was much interested in history of science and collected a lot of old writings and mentioning of meteor storms, fireballs, and everything that had to do with meteors from the past. In fact, everything that we know about past meteor observations, meteor storms, fireballs from centuries ago, much of this we know thanks to this Kettler. In going a little bit further into the 19th century, we get at the Perseid comet return in 1862, which was surrounded with a number of years with very rich Perseid returns that attract a lot of attention. The Leonid parent comet returned, and we had these Leonid storms in 65, 66, and 67 in the 19th century. We can say that about 160 years ago, that was the start of meteor astronomy. And a number of very few professional astronomers invested a little bit time into it, but the main work was done by a British amateur with the name William Denning. He was specialized in observing visually meteor showers and especially minor showers. He tried to determine radiance, just like Global Meteor Network does today, but he didn't have the tools we have now. He had a globe, a black star globe, on which he plotted the meteors he saw with chalk. That was a very, very poor accuracy, of course, and the results led to a lot of controversy. We have to wait, in fact, until after the Second World War, before we get a little bit more real science done on meteor work. Bernard Lovell, for instance, at Jodrell Bank Observatory, started systematic observations by radar, backscattered, to measure velocity, to determine trajectories, radians, and orbits. And that was a little bit regarded as the holy grail for meteor research, but people misunderstood one thing, and that is that radar observations in that time were rather poor accuracy. So it was a little bit misleading to think, oh, let the radar run, we don't have to look at meteors anymore, because the results were really, really poor in quality in that time. The very first really serious project for meteor research, that was in the 1950s because of the space race. They had to make some risk assessment for meteoroids. Would it be possible for astronauts to survive in space? And that was an American astronomer, professional astronomer, Fred Whipple, who got a program to conduct with Super Schmidt meteor cameras that were installed in New Mexico. In 1959, the first test equipment was installed, and then during 3 years they collected meteor data. Can you imagine here this big device could do only a part of that what your small RMS camera can do. The Super Schmidt camera project was suddenly stopped in the mid-1950s, and in fact meant spaceflight started without a proper risk assessment. It was just, let's take the risk. The Meteor program had only permitted to determine a limited number of orbits, 413, and that left a lot of uncertainties. The program was just too expensive and too time-consuming, and that was the reason why it was shut down. And then came a time as if meteor astronomy was not necessary anymore. In the 1950s until somewhere in the 1970s, meteor astronomy was very, very unpopular. I can recall an anecdote for that. Professional astronomer Bertel Lindblad, he was more afraid to tell his father, who was also a very famous astrophysicist, specialized in galaxies. He was afraid to tell his father that he was going to make his PhD into meteor research. His father blamed him for choosing something in astronomy that could be compared like a dust cleaner of the solar system. So it was not popular at all in that time. And in fact, in the 70s, meteor observing was left over to amateurs, mainly. And there came a new generation. That was when I got started with meteors. And on the photo, you see me, a little bit like Denning, with plotting maps, trying to note with a pencil in the night the meteors I saw on a star map. We got the same problem like Denning had about in the late 19th century. The accuracy, we had too little data, and the accuracy was too poor of what we had. So we tried a little bit with photographic meteor work. But if you can imagine just measuring a single negative with a meteor, doing the calibration of the reference stars with such a machine, a size table, that took between 1 and 2 hours for a single meteor to measure. That was first too time consuming, and secondly, buying all these film, developing all these Kodak 3X film was also very expensive. So was also not the best thing to do. Professional astronomers had successfully used TV observations in the 1970s, but this hardware was absolutely too expensive and too complex for amateurs. In the 1980s, amateurs started to experiment with image-intensified video cameras like this setup in 1988 for the Perseus. Well, in fact, all these equipment could do less than what your RMS camera can do now, today. Big problem in that time was data reduction. We could record meteors, but what to do with the images, what to do with the data. we got. We were not even able to calculate precise positions for all this. We had to wait until somewhere in the years 2000 before video meteor work really developed. And here you see a map with the main video networks in the world. We had the Croatian Meteor Network that was among the very first to get expertise in this domain, and this expertise was later used for CAMS and Global Meteor Network. The Japanese developed their UFO capture software and developed their Sonatako net for meteor observing. In Europe, several regional networks made the Egmont network, using also the UFO capture program. And then in 2010, the CAMS, the professional CAMS project, was started by Peter Genetskis. And CAMS also allowed amateurs to participate. And then last but not least, Global Meteor Network got started in 2018. Now let's go and look at the results we had last year. 451,000 orbits collected, that's enormous. 425 new meteor cameras were, 425 different meteor showers were identified among the orbits we collected. And as many as 430 new meteor cameras were added during a single year, getting to a total of over 1 million orbits. Now, if we want to look how we compare, how does Global Meteor Network compare to other main networks in the world? I made a little table, and you see in the recent year, Global Meteor Network almost got as many orbits as the professional CAMS network. And I think this year, both networks will collect more than 500,000 orbits. The data from Global Meteor Network is also used in some of the CAMS networks. So the more data Global Meteor Network collects also benefits for CAMS, as this data can be used for CAMS. You see, compared with Egmont and Sonatako, we have quite a lot more data. I made a little table to show how the number of cameras evolved from month to month, from year to year. And you see the number growing month after month until we got at 1,067 cameras actively contributing to paired meteors in December 2023. There are a number of cameras that didn't contribute any data anymore during all these months, but it's still an impressive number of cameras contributing. Now, where are the really biggest contributors to the Global Meteor Network in 2023? Well, at the top is the United Kingdom with a distinct number of 261 active cameras covering a wide area around Great Britain. In the second place, we have the United States with 128 active cameras contributing. Over a giant surface, because there are even a few cameras here in Alaska. And here and there we see new cameras being installed during 2023. There is a huge concentration here in New Mexico, Arizona. Southern California is very, very well covered, and that's a real gold mine for Global Meteor Network data. We had also a very interesting development, a very, very quick build-up of a network, a dense network with a very, very dense coverage in South Korea, with 125 active cameras installed in less than 1 year, if I remember well. And that's a very important hub, because at this longitude, we do not have many cameras available. And with such a network, the northern hemisphere is well covered at this longitude. In the southern hemisphere, we had a similar development in New Zealand, where as many as 111 active cameras contributed to paired meteors in 2023. Going to Australia, Australia is a huge country. And in fact, It's almost bigger, I think, than Europe. There you have mainly in Western Australia a big concentration of cameras, also being a gold mine for data. And on the eastern part, in eastern states of Australia, we see also more and more cameras emerging. And finally, last but not least, the one I will mention is Canada, where originally the network started together with New Mexico. There we have 67 active cameras and more than 16 that didn't contribute in 2023 anymore. Now, I will not go further into detail in the numbers because the report of the Global Meteor Network has been published and can be consulted on eMeteor News. You go to the site and you will find the report with the maps for all the countries, all participating countries, all the tables, all the numeric details you can read there. I'm not going to bore you with this. Furthermore, in last year, we had a number of discoveries, let's say, inactive showers that suddenly flared up and gave some unexpected activity. We had a few new showers that we could identify. And for instance, at the end of 2023, Global Meteor Network detected the very first meteors from comet Virtanen, which was really a very exciting event. Now, a few points for the future that I can think about. What I see is that where regional coordinators are active, the Global Meteor Network is doing really very, very well. So I think if we can get more people taking up a kind of coordinating role in certain regions, that would definitely help to develop the Global Meteor Network further. The network health stages and technical support are very necessary because people tend to let their camera run in automatic mode, and even after, if it fails, it can happen that 1 or 2 weeks they even don't notice that their camera doesn't work anymore. So there are developments to monitor the health status of all the cameras to keep everything under control and prevent that we have dead cameras or that camera operators are not aware there is a problem with that camera. For the global coverage, we absolutely need more cameras in South America, also in South Africa. The southern hemisphere longitudes need better coverage. Then for the scientific reason, it's important that there are two independent networks like CAMS and Global Meteor Network. It's not competition. It's very important that if Global Meteor Network or CAMS discover something, that an independent network can confirm this find. For science is very important.
Well, we're a bit over time. I'm going to ask you to wrap up as soon as possible. Thank you.
Okay. So we have to pay attention for outreach and we have to document results. So I suggest please write reports about fireballs, about achievements, and we can do that in Meteor News, which has a new address and new hosting. Maybe others have more suggestions. So my conclusions: to fully understand the magnitude of the Global Meteor Network's achievements, it's necessary to look at this in the historic perspective. How poorly was meteor work developed, let's say, until about 20 years ago? It may look for people that's all to be taken for granted, but reality is a little bit different if you look in the past. The Global Meteor Network is the most successful project ever undertaken with amateurs and volunteers, thanks to the efforts of many people, but one person in particular, Dennis Vida. So thank you, Dennis, for what you have created, because you made a dream come true that you could only dream about in the past. Thank you.
Well, thank you, Paul, for the kind words and your hard work as well. We are very short on time. If you have any questions, you can put them in chat for Paul, or you can discuss them during the break. But next up is Logan. Logan, are you here?
Yes, I'm here. So
awesome. Thank you so much.
getting this set up, I'll introduce myself. I'm Logan Cordanier. I'm a PhD student here at the University of New Mexico, doing work on persistent trains, which is what I will be talking to you about today. So let me get this set up. Doop-a-doo. Okay. So what is a persistent train? This little looping video here demonstrates an example of a persistent train, but essentially it's a long-lasting glowing trail that can sometimes be seen after some meteors. Like the name suggests, they last anywhere from minutes up to an hour or so at most, and they emit over a wide range of wavelengths from infrared, visible, ultraviolet, perhaps even radio. The light is produced from chemical reactions, so metals in the meteor react with ozone in the atmosphere, at least in the continuum phase, which starts a minute or so after the meteor. I've shown here an example chemical reaction. So iron reacts with ozone to produce iron oxide in an excited state, which then de-excites and emits light that we see as the persistent train. This iron oxide can react with atomic oxygen, and it kind of recycles the iron so it can react anew. And just to stress, these are self-emitting, so it's not due to reflected sunlight. So in case your internet was a bit choppy, I also have still frames here to kind of give an overview of what's happening. So this shows 6 seconds up to 3 minutes past the meteor. And you can see how its shape has been distorted by the winds. There's bright structures that form. It gets more puffy as it diffuses. It has a very complex and interesting morphology. So to give a bit of background, catalogs of persistent trains have been made in the past. The largest was compiled by Olivier back in the 40s and 50s, and he had over 2,000 persistent trains in his catalog. More recently, Japan's Metro campaign in the 90s and early 2000s found a couple hundred more persistent trains, mostly with a focus on the Leonid outbursts at the turn of the century. And then there were quite a few studies done on the Leonid outbursts themselves, with a few case studies and handful of meteors being examined at a time. Now, while these catalogs are very useful and important, they have a few issues if you want to try to do statistics on the persistent trains. The first being that they relied on human observers, which naturally gives a bias towards meteor showers. More people would be out and about taking pictures, looking up at the sky during a meteor shower than they would on some random Tuesday in the summer. A lot of these early catalogs were also compilations, so it relies on lots of different observers reporting to a centralized source, which might have different, detection techniques or analysis pipelines. So it's very non-standardized. And again, they focus mainly on the brightest type of meteors because those were most associated with producing persistent trains. So because of these prior catalogs and research, mostly arising from the Leonid outbursts, we have some assumptions that have been made about the meteors that make PTs, namely that the fast and bright meteors are more likely to leave persistent trains, and that the persistent trains always form in the brightest part of the meteor. Again, these assumptions are heavily influenced by the Leonid outbursts. So this is where my research comes in. Here's our camera setup, the wide field persistent train camera, second edition, whipped 2. We have a fisheye lens on top of a CMOS sensor. We've deployed at Sevietta National Wildlife Refuge here in New Mexico, in a semi-remote part of the state. And we had our first observing campaign for nearly 2 years. The camera is configured to take 5-second exposures with a 1.5-second readout time, and we required that the sun and moon be at least 15 degrees below the horizon in order to ensure that the skies are nice and dark above us to get the most sensitivity. And then the camera and all the electronics were put inside this tiny mini fridge that was thrown up on top of a roof. You can see the dome there, and the little silver rectangle there is the sunshade that opens and closes like a clamshell to protect it during the daytime. And then here's an example image from this camera system, pretty typical. You can see the band of the Milky Way. There's a meteor in the top right corner there. I'll briefly go through how our detection pipeline works. So I've written a code that automatically identifies Meteor and persistent train candidates. It does this by using a series of 3 consecutive images and essentially looks for things that flash bright for a single frame and then disappear. And we use that technique instead of straight subtraction because it's better at filtering out clouds. So for each potential candidate, we fit an ellipse to it and can get a variety of parameters like its centroid, major axis length, and orientation. And all that is useful because it helps us filter out airplanes, which are a major concern for this setup. So to filter out airplanes, we check several things. First, that 2 potential objects are located close in time, that they're a reasonable distance away from each other, that they aren't doing any weird 90-degree U-turns. We're not looking for, UFOs or anything, and that their lengths are comparable, meaning it has about the same speed. And then if a particular hour of observation looked too cloudy, we just skip the entire thing because it wasn't worth the headache of trying to sort out thousands upon thousands of potentially cloudy sources. So now the efficiency, we found about 800 some thousand objects over the 2 years of observing. About 500,000 of these were airplanes and were auto-filtered out by the pipeline. Another almost 400,000 were clouds and were also ignored, which left 38,000 or so potential candidates that had to be manually reviewed, each and every one. And of those, almost 30,000 were false positives. So things like lightning on the horizon flashing and causing clouds to light up, planets scintillating with thin clouds passing in front of them, airplanes that somehow managed to slip through anyway, and bugs crawling on top of the dome, kind of look like meteors apparently, which left about 7,500 actual meteors, of which only 850 had trains. So quite a lot of not what we were looking for, but that's the way it goes. So now here's where the Global Meteor Network swoops in to save the day. We cross-referenced all the meteors we found with the Global Meteor Network database, which, I don't have to say is incredibly useful because all the hard calculations were already done. We just got all the parameters for each meteor that we matched in time and sky location. So as mentioned earlier, New Mexico is a great place. It has good Global Meteor Network coverage. The map to the right there shows the WIP2 camera at the star, and the blue dots are other Global Meteor Network cameras in the area. So about 70% or so of the meteors we found with the WIP2 were co-detected by the Global Meteor Network. And of these, 637 left trains, for a whopping 13% of the observed meteors in the Global Meteor Network database having trains that we observed. So I'll go through some of the results. I can't go through all the results. I don't have time, and I can't go into great detail of the ones I do choose to present. But it's important to stress that they were all made possible through the Global Meteor Network data. So this plot here shows the average velocity of a meteor versus the peak magnitude of the meteor that produced the persistent train. The red dots are the meteors that left persistent trains, and the gray dots are ones that we didn't see leave persistent trains. So most of the research that had previously been done had seen persistent trains associated with meteors brighter than -2 magnitude, which is below this gold line. And as you can see, the vast majority of our meteors were above this line, dimmer than magnitude -2. So we're looking at a new and different population compared to previous studies. We can also kind of look at the terminal height. So this is how far the meteor penetrated down into the atmosphere. And I've broken it apart here by slow and fast meteors, depending on their speed. And we can kind of see that there's a cutoff around 93.5 kilometers. So anything that ended above that altitude tended to not produce a persistent train. And that's really useful for us because it allows us to filter out meteors that have the potential to leave PTUs from those that don't. And we'll get more into this altitude dependence here in a bit. So we can also look at the range where the persistent trains themselves are formed. We looked at 100 or 60 so individual meteors and mapped out where the persistent trains occurred within the meteor. So the meteor is the gray bar, the red and blue are the start and end locations of the persistent train, respectively. And of particular note is the little yellow dot shows where the meteor itself was the brightest. So we can see right off the bat several instances where the persistent train doesn't overlap at all with the region where the meteor was the brightest, contrary to one of the previous assumptions. We can also look at individual meteor showers. So in this left-hand plot, the little diamonds each represent a different meteor shower plotted against their average shower velocity. And we can see that the slower showers tend to produce a larger fraction of persistent trains. This trend is also mirrored in the sporadic meteors, which are shown in the connected solid line. And if we look on the right-hand plot, again, I've broken it apart by individual meteor showers based on their average shower velocity and the altitude range that each shower is typically found at. The gray band also shows the zone where we typically found persistent trains. So we can see that the ones that overlap the zone have a high number of persistent trains. And also there's a trend with as velocity increases, the altitude range of the shower also increases, which explains why the fastest showers tend to produce less persistent trains because they aren't reliably making it down into the persistent train region. So now kind of tying things together, I've hinted that the persistent trains occur in a relatively narrow region of altitude. So this plot, the top panel, shows the altitude range persistent trains are typically found at in the shaded blue region, along with their parent meteors in the shaded red region, and the total populations in the shaded green region. And if we look at the bottom panel here, this shows the ozone volume mixing ratio, or the fraction of ozone molecules in any particular given volume of atmosphere. And we see there's quite a big bump, which is known as the secondary ozone maximum, that aligns quite well with the range of persistent trains. And this isn't an entirely surprising connection. The equation I showed you earlier explicitly depends on ozone, so we'd expect to see a connection between these two quantities. So because of this, we might be able to use persistent trains to detect ozone. So we did exactly that and looked at the connection between ozone and persistent trains. So this figure here, the gray line, shows the variation in ozone in that secondary ozone maximum, along with its kind of one standard deviation range in the shaded region. Now on top of that, we've overlaid the percentage of sporadic meteors that left behind persistent trains. And we can see they're correlated extremely well, which tells us with a bit of work, we might be able to use the occurrence rate of persistent trains among sporadic meteors in order to predict the amount of ozone present in the secondary ozone maximum, which is a super neat result that hasn't been seen before. So why sporadic meteors and not meteor showers? This plot here kind of shows the trend with the red dots indicating the sporadic meteors. And we can kind of see there's a nice kind of linear upward trend with as ozone increases along the x-axis, the number of PTs increases on the y-axis. Nice trend. However, when we look at the meteor showers in the cyan squares, we see they're way more over the place, which is why they aren't as great for estimating ozone. But what this does tell us is that there's an importance to the individual meteoroid properties, such as composition, how strong they are, the dynamical origin, which are homogeneous for each shower, and that seems to play a very important role in determining whether a persistent train forms. So it's not just the ozone that's important, but also the composition of the shower. So just to give a glimpse at what we've got in store, we're going to be deploying a few new instruments to help with our persistent train characterization. We'll have a hyperspectral imager, which will allow us to get spectra of the meteors and the persistent trains. We plan on adding 4 new global meteor network cameras of our own to kind of increase our coverage. We'll have a steerable mount that'll be able to slew to the location of a meteor with a video camera, spectrograph, bandpass filters for iron and magnesium, and then a plain Jane camera. We also have another WIP2 station already built, also in a mini fridge that we'll throw somewhere else out in the desert and hopefully do anti-coincidence measurements between the two. So just in summary, our catalog is kind of better than previous ones because we use the same camera, the same reduction pipeline, the same detection pipeline. We pulled all our data from the same database, which gives us a large degree of uniformity and standardization compared to the previous catalogs. We also tested some of the assumptions and found that fast and bright isn't a necessary condition in order to form persistent train. In fact, the dim and slow ones seem more likely to leave persistent trains. And we also saw that it doesn't have to form in the brightest part of the meteor. Lastly, we found a super neat result where the sporadic meteors can be used to estimate ozone content in the mesosphere lower thermosphere region, that secondary ozone maximum. And then just end by saying the results I presented here are going to be submitted for publication very soon. So if you're interested in learning more, just stay tuned and you'll be able to read all about them very soon. And with that, I'll end here. Thank you.
Amazing work, Logan. Thank you. We are, again, short of time. So any questions, please put them in chat, and we can also answer questions during the incoming break. And next up is Damir Shagon. He's here, but he sent me a recording. So I will show his recorded talk, and just give me a quick second here so I can pull it up. Thank you, Logan. Again, while I'm doing it, if anyone has a question for Logan, please go ahead. Just need to quickly pull up Damir's talk.
To sort out show number.
Oh, there we go. Okay. Well, Logan, I think there might be a question for you in chat, and I will share my desktop here, and you or someone, please tell me if you can hear what Damir is saying in the video. So I'm going to start playing it, and if you can hear it, someone just send like a thumbs up through Zoom, and that's it.
In this presentation, we will briefly show how can we check out if what we see as a group of radiants on daily meteor orbits plot actually represents a new meteor shower, or it is known one having its actual activity and orbital data poorly defined. Since its beginning, the global meteor network is constantly growing up. As a result, during October of 2023, it reached an important milestone, its first million of orbits. Such a few of meteor showers, their activity periods, and possibly new meteor shower hasn't been seen up to now, thanks to the fact that all GMN orbits data are public. At the end of each month, once all orbits were computed and monthly plots showing activities of known meteor showers being produced. In this way, we may see rough activity of a certain meteor shower, since from the plots we can't know when some of these radiant groups of known shower actually occurred. Plots refer to coordinate system solar longitude minus radiant ecliptic longitude as for longitude, and radiant ecliptic latitude as for latitude. At the end of each day, once all orbits were computed, a daily plot showing activities of known meteor showers is being produced. In this way, we may see activity of a meteor shower, knowing the solar longitude, thus having defined its position with precision of 1 degree of solar longitude. As in the case of monthly plots, known showers being active according to GMN sources are marked with a circle, dimensions of which actually represent measured dispersion of a specific shower. Not all showers have their dispersion estimated, since it requires a substantial number of orbits, meaning some showers have some default circle diameter of 3 degrees. Now suppose you see a group of radiants which are not marked with a circle, meaning it is not being recognized as a known shower. Does it mean it is a new one? And how can we ensure that we are not rediscovering the wheel? For example, the marked group of radians looks suspicious to you, and so what to do? There is a simple tool Ivica Skokic built more than a decade ago just for this purpose, the Croatian Meteor Network Shower Stream Search. It allows search of meteor showers by reading current data from the IIU MDC database based on parameters like air ascension, declination, longitude, latitude, including all orbital parameters. In order to use the tool for given daily plot, we should first estimate the position of the radiant, namely to read coordinates from the plot. In this case, we may be pretty sure that the radiant group is inside 270, 300 of longitude and plus 30, plus 45 latitude for given solar longitude, 151, 152. Indeed, in case we submit data as estimated, there won't be any resulting shower and we could conclude this is a new one. However, since the activity period of non-showers is not always defined in the database correctly, we may rely only on data given for maximum of meteor shower activity. Thus, the solar longitude data should be within enough to cover the solar longitude of the maximum. One of common errors is related to negative values of radiance ecliptic latitude of declination. Minus 30 is not smaller than minus 45, for example. Such query will yield no results for sure. In this case, we can see that radiant we examined actually represents late Perseids. In case we can't match the group of radiants with known ones according to IIU database by radiant position, we may do the search based on orbital similarity. A Python script similar to the one used for detection of new showers during past couple of years may be used. It may be based on exascending declination or other coordinate system. In this case, we will use the same data as for stream search tool. The left plot shows distribution of radiance based on the criteria, in this case Drummond, but anyone may do, for orbits inside 5 degrees from given center for given solar longitude interval. The right plots represents the distribution centered at radiant position corresponding to data from most prominent being in the distribution from the left side. For data having distribution similar to Rayleigh distribution, the value for fitted distribution at 95% may be picked to sort out shower members. If the distribution doesn't satisfy Rayleigh distribution, as in this case, then an arbitrary criteria value may be picked as shown on the plot on the left side. It is good to plot non-shower members to see if the sporadic meteor background looks unaffected by shower members extraction, the plot on the right. Shower meteor plot visualize what should be meteor shower members based on picked D criteria value. The PE plot may shed even more light in sense of estimation if D criteria value picked looks good enough. Activity plot for given solar longitude helps to estimate the duration of possible new shower. In this case, we found that there is similarity of orbits with the meteor shower of Perseids, since the D criterion cutoff of 0.11 is larger than the criterion similarity of possible new shower and existing one, which would be 0.09, and it's reasonable to conclude that the meteor shower in the case isn't new, but meteors belong to Perseid shower. Remember, a group of radiants not marked as a meteor shower on radiant plots doesn't always mean what we observed actually is a new meteor shower. Thank you for your attention. We hope you try to use the CMN shower search tool more often and do basic search on new meteor showers yourself.
Okay, so that's Demir's talk. As you can see, he's very interested in meteor showers, and I think he has a couple of ideas for what we're going to discuss during the workshop. But now I'm opening it up for any questions for any of the previous speakers, and if there aren't any questions, we're going to take a break. Also, we do have breakout rooms. So if there's one person in particular you want to talk to, you could put yourself in a breakout room with that person and you can discuss a certain thing. So opening up for questions, and also if there aren't any, we're going to be back in about 10 minutes. It's going to be 17:05 UTC. So that's about it.
So anybody still here? Lots of participants, but everybody seems to be running away, right? Ah, Len, I see you are there. Will Joy, okay. Gosh, I don't know you people. Where are you all from? I'm in the Netherlands.
Hello,
Okay.
I'm from Croatia.
From Croatia. That's not too far away. That's great. Guess Will, you seem to be on Mars, right?
No, I'm here in Edinburgh. So,
Oh,
but
that's not too far
that's just
either.
a photo I took a number of years ago.
Oh, yeah, exactly. Yes, all right. Yeah, I think that's Edinburgh is even closer than Croatia from the Netherlands, I would expect, as the bird flies.
Absolutely.
Yeah, I just joined. I came in late. I didn't realize the meeting is on until I went to my computer and saw the reminder that apparently reminded me already 6 hours ago. I don't know how long. So hope everything is good in the meeting.
Yeah, but you have a chance to join the meeting for Southern Hemisphere.
Yeah, okay, true.
I went to both meetings last year.
Okay.
I think it could be a very long session, but enjoyable. There's some interesting talks for the Southern Hemisphere section as well, actually. So see how it goes.
Well, I'm from the Southern Hemisphere, so for me, it was a 5 a.m. local time start. So I'm a bit bleary-eyed at the moment.
Okay, that's not good either. But you know, this is the problem with a global Meteor network. How do you get a time slot that suits everybody? It's impossible.
Absolutely. Pretty good for Edinburgh, though, on UT time.
I think having it on the weekend, though, makes it a lot more possible for more people.
Yeah, I think so too. Yeah, true.
We'll put suggestion to Dennis Vida to for next year to put informal chat during breaks.
I think he suggested that, didn't he? He said if there's one particular person you want to talk to, meet in one of the breakout rooms. So we would have that possibility, but I think there's nobody in a breakout room anyway. We're all here. This is what I noticed during the pandemic too, that during the coffee break people run away, but I think it is a chance to talk to people. Like Paul, I haven't seen you for a while. Good to see you.
Hey, Detlef.
I've just popped up the breakout room, GUI or whatever you call it. And yes, you're right, there's 5 rooms, but there's no names against them, so I don't know which room to join to speak to someone.
Yeah, that's true. Yeah, that's a bit the issue. I think the meetings, they do. Okay, so there's no name if you have a room. No, you just see there's one person in the room, but no, it's me actually. Why does it say I'm in a room? I'm not in a room.
Oh, hi, Detlef. It's been a while.
Hi, Dennis. Yeah, it's been a while. Good seeing you.
Hey, you too.
I just
Yes,
joined.
we have this rack cheers meeting. If you're familiar with this from Ham Radio, rack cheers.
Ah, no, I don't know that. What does it mean?
People on Ham Radio who like to talk about non-technical.
Okay. Yeah.
I looked into getting like a Gather Town or some other service for the meeting, but those things are quite expensive. So I decided just to use breakout rooms and other things. But maybe when there's more money, we could afford a nicer experience. Yeah, good. We have 5 more minutes before we start the other talk by Luke. But if someone wants to formally introduce themselves now, I think now is the time. We did have a short introduction session at the beginning. I don't know, Detlef, if you were there for that. If you would like to introduce yourself now, very quickly, please go ahead so people know who you are.
Yeah, no, I just joined, so I missed the introduction section. Okay, I'm Detlef Koschny. I currently am in the Netherlands. I live part of my time in the Netherlands, part of the time in the southern part of Germany. I used to work at the European Space Agency doing Meteor stuff in a, well, sort of professional way. Now I'm back to being an amateur. I retired from the agency. I'm not yet operating a GMN camera. Shame on me. I have some other Meteor cameras. None of them are operational right now. I think I need to do more work on them. So that's my brief introduction. Actually, what I'm mainly working on right now is lunar impact flashes, trying to do that. And I had a student build a little device that tracks my telescope to the moon, which normally it doesn't work as well as you think. And it uses a little Raspberry Pi. So if anybody's interested in that, that's what I'm currently working on. Not so much meteors, but something very similar, I think.
Amazing. Thank you. That was really cool. Murray, go ahead.
Yes, as you heard earlier, I'm from the Southern Hemisphere. I actually have a doctorate in astronomy, but I'm an amateur as I never found a job in it. My main interest is seeing if I can write a bit of code to do good photometry using our network, because the bright stars that we can see are significantly neglected in terms of looking at variable stars in photometry. So it's a great resource for that.
Absolutely. There was a person from Ireland who wanted to do the same thing. I can probably put you in touch with him, who had a similar idea of detecting stars into cameras and doing tracking their magnitudes over the long run to look for some variability. Thank you for the introduction. We have 1 more minute before next talk. If someone wants to introduce themselves, just raise your hand in Zoom, and I'm going to call your name.
Brilliant question for you. You
Yeah,
you have those deers like last year. So the meaning is you are still working at the university.
No, it's from IKEA. I'm at home, so you can probably find these at your local IKEA. They have them everywhere. Okay, so Luke, you might want to start sharing your screen and getting ready to
All
to the
right.
talk. I think it's just in a few seconds, so I think you can even start. So go ahead.
Hi everyone, I'm Luke from Phoenix, Arizona. Hopefully I'm not the only one out there without a PhD. My day job is an airline pilot, so no PhD required for that. Let me see if I can share the screen here. Like this.
We can
So
see
I'm
it
going to
looks
talk.
good.
It looks good. Okay, cool. So I'm going to talk about a project I've been working on for about 10 months now, obsessively. So about 10 months ago, I didn't know anything about the GMM network or anything about Meteor, really. So my project, what I've done is that I'm using the RMS camera system that I have modified to add airplane position data overlaid on top of the images. So it creates, let's see if I can start this video. Here we go. So it creates time lapse twice a day, so one during the day, one during the night, and adds aircraft position data overlaid on the images. So this is an example of a time lapse during the day. And if I pause it, you can see the type of data I can overlay. So I can overlay altitude, aircraft type, etc. That's what it looks like for night capture. And so what's the motivation? Why am I doing that? By the way, I can pause on this and you can see the aircraft lights line up pretty well with the targets here. So why am I doing that? Aviation is responsible for about 3.5% of climate change. And it turns out that out of that 3.5%, about half of it is coming from contrails. So the contrails that airliners leave behind from time to time are mostly responsible for the climate warming impact of aviation. So it's not my idea, but what would happen if we could cut if we could stop laying contrails? We would then be able to cut half of the warming impact of aviation, and we could do so pretty cheaply and easily, relatively speaking. We would not need to change our equipment, so the current fleet of aircraft and equipment and engines would not need to be changed. We could do so extremely efficiently, about 50 cents per ton of CO2 equivalent, which, for example, solar panel is about, depending on who you ask, it's about $10 per ton. Nuclear power plants about $60 per ton. So here we're talking about a very cheap way to remove a lot of CO2 equivalent out of the air. We wouldn't have to change the travel habit, although I'm not saying we shouldn't, but I'm saying this solution doesn't require that. And if we did so, the result would be immediate. So there's no lag. So if we stop producing CO2, it would take centuries for the effect to be felt. But if we stopped laying contrails, the effect would be immediate. So as I said, I don't have a PhD. So what are contrails? They're obviously just water. It's actually ice. And where is the ice coming from? Well, it turns out that of course when we burn fuel, we break the bonds between carbon and hydrogen, and I did the math, and 3 kilograms of CO2 and 1.283 kilograms of water does not add up to 1 kilogram of fuel. So obviously the extra weight is coming from the carbon and the hydrogen recombining with the oxygen in the atmosphere. So for each kilogram of fuel that we burn, we produce about 3 kilograms of CO2 and about 1.2 kilogram of water, which when an airplane flies through a region of the atmosphere that's super saturated in ice or in water, will produce contrails. So super saturated means that the mass of air is containing more water than it can hold, and it should condense, but it can't because it needs a little energy bump to do so. And when an airplane flies through that zone and adds water to it, and condensation nucleus from the particulate emission of the combustion, it creates a contrail. So if it's just water, why is it bad? Think about a cloudless night versus a cloudy night. Obviously, the cloudy nights are much warmer. It's the same phenomenon, although it's actually very complex and above my pay grade. So there are paradoxical effects of where is it? So there are paradoxical effects of contrails. On the one hand, they reflect shortwave radiation back to space, which has a cooling effect. On the other hand, they trap heat by absorbing and re-emitting shortwave radiation. Although the net impact is a strong warming effect. So what can we do about it? This is more of my area of expertise as an airline pilot. We can change flight altitude. We can reroute airplanes around zones of contrails formation. We can try to use fuel that produce less particulate matter, which provide condensation nucleus for ice to form around. I put a little asterisk there next to the first two mitigation measures. Changing flight altitude and changing routes, although it would reduce the net warming effect of a flight, it will produce more CO2, burn more fuel, and cost more money. So if we were to do this, we need to get it exactly right, or very close to exactly right. Otherwise, we may do more damage than good. See if I can really quickly switch to the browser. So I apologize if, let me know if let me know if you guys see this yet. So share.
See the slides.
You see a slide, but you don't see the.
You don't see the browser. No, you might want to reshare with the screen shared instead of the.
Okay, I see. There we go. All right, I got it there. So here I switched to browser, and this is a website from an organization. I'm not affiliated with them. It's a breakthrough energy organization. They created a website, contrails.org, that has a wonderful visualization tools and model software tool to model contrails. So they put this wonderful website that shows flights and their associated contrails. Red contrails are heating, and white contrails are cooling. For example, this is what it looks like in Europe on that particular date. Massive amount of contrail, persistent contrail forming together, creating a strong warming impact over Europe on that day. So it's a localized effect, but it's a very strong effect. And you see here in blue, in the morning, those contrails reflect light back to space and are actually cooling. So we could potentially even use contrails to create a cooling effect. Back to my slide. So yeah, the website is contrails.org. I would highly encourage anybody interested to check that out. So the challenge from operators and airline perspective is, are the models right enough to be used for operational decision? So the main model that is being used is called COSIP, Contrail Cirrus Prediction Model, and it's been validated with a flight testing campaign, satellite imagery. But what's needed for operational decision, in my opinion, is a fine-grained validation of those models. And that's where my idea was to use some GMM cameras to create a data set of flights and contrails. So those cameras would make recording and observe the formation of contrail or not, and compare that to a COSIP model to actually validate how good that model and how useful it would be for airlines and operator to make decision based on that. So the data set would create flight contrail pairs in fine spatial and temporal resolution from ground-based camera. And we could combine that with satellite imagery. The problem with satellite imagery is that it's very hard to attribute a contrail to a specific flight from satellite imagery. So if you could get the data initially from a better source and then transition to satellite imagery, it would be very useful. So here is an example, a research. I just pulled that out of my database a few days ago. So this is a few hours of recording and about, so I should pause this and explain a little bit. So green airplanes are planes that are flying at very low altitude and don't have the potential to create contrails, and red airplanes are flights that are flying at higher altitude. And what I'm doing here is I'm noting which airplane is causing a contrail and which airplane does not cause contrail. And let's see. It's a pretty long video, so I'm going to fast forward. So about 27 airplanes are flying through the field of view of the camera throughout the day. And at the end of the day, what we have is that most altitudes do not produce contrails except two specific altitudes, 33,000 and 34,000. So if there was a way to know this in advance, it would be pretty easy for airlines to decide to change altitude. I mean, we do it all the time to avoid turbulence. We could do it as well to avoid contrails. So where is the aircraft data coming from in my time-lapse overlay? It's coming from a very cheap little box I've hooked up to my Raspberry Pi. So that cost about $40. It's an SDR receiver with a little antenna, actually pretty big antenna that I have on my roof, but you don't need a big antenna. So it's ADS-B stands for Automatic Dependent Surveillance Broadcasts, and that provides live aircraft data position from all civilian airplanes and most military aircraft except fighter jets. It's unencrypted, and the range of one receiver would be about 50 to 350 kilometers, depending on the size of the antenna. I record day and night. So one thing that was a little bit of a challenge initially is to record during the day. Most of the GMM cameras infrared filter has been physically removed, and during the day, that's a little bit of a problem. It's not a showstopper, but it's a little bit of a problem. So I've installed a $5 little infrared switcher on my camera. It puts and removes the infrared filter automatically. So it removes it automatically at night and puts it back in automatically during day observation. Very cheap. So how did I modify the RMS software to do this? one thing I had to do is to add 2 new functions for the transform from image coordinate to horizontal coordinate and back.
Luke, just a heads up, we're a bit over time, if you don't mind.
Okay. Ooh, yeah.
Thank you.
And man, time flies. So there was when I did that, I immediately had some issues that I noticed. And Dennis, you're probably going to talk about this later on, this timing issue.
We can discuss it during the workshop, definitely.
Okay, cool. And so there was some pointing drift issues due to precession error. Once corrected, the pointing drift during observation got a lot narrower. Again, I don't have a PhD, so I can put cat pictures in my presentation. There was a parallax error that was solved by adjusting the height specification of the station. And yeah, I think I'm out of time to explain this one, maybe for the workshop. There was a rotation error that was solved by changing one of the function in the code, rotation with respect to horizon. That was the big one, but it took me a few months to figure that out. So what's the benefit to RMS? It's a neat way to find a gross error since my meteors have GPS. So it's very obvious when things don't line up. There is a potential, and maybe that would be interesting for Logan as well, to dynamically create masking for airplanes. So it would be very easy to, instead of putting a target above this airplane, we could put a mask that would mask our airplane from Meteor data. Potential for Meteor to increase Meteor awareness. There are a lot of aviation enthusiasts out there that would love to run these cameras. All right, I think I'm out of time. So I just want to say thank you to all the GMN community, to Dennis in particular, and to Nick Moskowitz, who let me borrow his camera so I could try it out. And last funny point here, the first contrail was actually laid in 1919 by this guy, Franz Zeno Diemer, who took this biplane aircraft to 32,000 feet, looked behind him and said, "Oh, what is this?" And this was the first time anybody observed a contrail. And with that, I think we're out of time, so I'm not going to cover that. Any questions?
Yep. Amazing, thank you. Very impactful work. In the interest of time, we will go to the next presentation. However, what I've done is I've opened breakout rooms with individual topics. So who's ever interested in a certain topic, during the next break, you can go into breakout room and discuss. And I also asked the speakers to go to that breakout room, so if anyone has any questions for them. Okay, so next up is Jamie Shepard. Jamie, please, if you don't mind sharing your screen and starting your talk. Amazing work, Luke.
Okay.
We can see it. It's all good.
Good. I'm going to be talking about how we correct for gravity in the analysis of long duration fireballs. The picture on the screen here is one that lasted about 12 seconds, taken with a fisheye from the roof of my house. And we're going to specifically be using the Western Meteor Python library analysis software, which, as everyone knows, was developed by Dennis Vida and colleagues. And let's take a look at the, all right, it's not advancing the slide. Let me just start that again. There we go. So here's a trajectory plotted on the ground map of Scotland. It was seen by 4 cameras, and I'm the little blue spot just underneath there. And if we take a look at it, there's the 4 images shown in the GMN camera output. Quite bright, went set to about -5, -6, and quite slow. It had a very typical asteroidal orbit, entry velocity of about 13 kilometers per second, and it penetrated to quite low altitude of about 30 kilometers. So it was definitely in meteorite dropping territory, although it probably only dropped about 20 grams or so, virtually impossible to find. So here's the analysis. Western Meteor Pi Library, WMPL, I'm just going to call it the solver from now on. And I'm only going to deal with the residual plots. So we have 2 kinds of plots. We have the line of sight residuals measured in arc seconds. That's how far the measured point differs from the fitted trajectory. And we have the spatial residuals, which are the distance between the measured points and the trajectory at point of closest approach in 3D space measured in meters. Now, if we compare the two, whoops, going back too many slides. I flipped out of the mode. What happened there? Anyway, let's go back to this. Yeah, there we go. If we compare the two, we can see that if we use the software with no gravity correction, we get the plot hugging along the 0 line. But if we apply gravity correction, then after a long duration fireball, it seemed to creep away from the 0 line. And we see a similar thing happening with the spatial residuals. Starts at the 0 line and then gradually it seems to drift away. Has to be said that this software is perfectly okay for any event with a duration less than about 5 seconds. This thing only seems to show up with longer duration events. Now we look at why that's happening. Well, first of all, fitting software likes to deal in straight lines, and the pull of gravity on a fireball causes it to deflect downwards towards the Earth's surface. So there'll be if you don't apply any gravity correction, there'll be 2 points along the trajectory where the fit is exact, and then it'll be not so good at the very tips, and somewhere along the middle it'll be not so good either. And that's what we see, that kind of red and blue arc there. You can see there are a couple of places where it crosses the 0 line, and at the beginning and end it deviates away. So I came to thinking that's not quite what I'd like to see in the gravity correction. Maybe I can try it a different way. Maybe I can work out by changing the altitude measurement of the measurements and then feed that into the solver without gravity correction and see what difference it makes. Now, fortunately, the output of the solver gives you the range to the fireball in the data report. So here we have a solvable triangle. The range from observer to fireball, the amount of gravity drop can just be worked out as half GT squared. We've got 2 sides and an included angle. We can work out the apparent drop angle. Comes out as an equation like this. And another very convenient thing from this point of view is that quite recently, a couple of years back, a data standard was established for sharing data amongst fireball networks and meteor networks generally. Now, it so happened that the one they chose to use was pretty closely what the Desert Fireball Network in Australia were already using. Now, they use seed coordinates of altitude and azimuth only. They don't worry about the right ascension declination. Now, that was perfect for our purpose, because all we needed to do was go into the ECSV file and somehow change the altitudes using our apparent drop correction formula. And we built an Excel spreadsheet to do that. There's all the columns, generated corrected ECSV data, fed that all into the solver, and here it is with the WMPL gravity correction on the right there. And here's this new method using correction of the fireball measured altitudes beforehand. And we can see that between the two, there it seems to drop away from the zero line, and here it seems to follow the zero line quite closely. And again, if we look at the line of sight residuals with the built-in solver, some of the results really creep far away, almost a moon diameter away from where we want them to be. But using this method, we get back down quite close to the zero line, quite a lot of the points there within 200 arc seconds. Now, to show it wasn't a fluke, here's another fireball the next month. That wasn't one we just did, was in October last year. Here's one in November, Southwest Scotland, 9.5 seconds duration. And if we run the numbers, there's the built-in correction on the left, and there's the pre-corrected altitudes method on the right. And as you can see, again, it behaves itself all the way to the end of the trail. With the spatial residuals the same, this kind of splay that you get with the built-in correction seems to go away. Now, instead of going into all the methodology for this, I'd point you towards an excellent paper by Dennis Vida and colleagues, which gives all the information you could possibly want about fireball and meteor analysis using the WMPL software. It's very comprehensive. It saves me going into any of it here. And if I compare, we then wanted to see if we could build this method into the software itself. So good was the documentation, I thought, well, I'm not really a Python programmer, but I thought I could just about give this a go if I can find the right place in the software. So eventually I managed to figure that out, correcting the altitudes within WMPL, and I managed to get the two plots, the XL plot and the WMPL plot, to match within about a meter, which is not bad. I then got to thinking, why are these gravity corrections not quite working out? And I suspected that part of the reason was that when we fit the points and then correct them for gravity, that the gravity drop vector is not parallel to the point of closest approach vector from measured point to trajectory. So the green lines are the points of closest approach vectors. The orange lines are the gravity drop that we're using. And as you can see, as the gravity drop increases and curves away from the straight line, so-called state vector model trajectory, the fitted points drift further and further downrange. And because the difference between the blue spots and the green spots is what ends up as being our residuals, we're going to see an increase in residuals as we go along. And here's the algorithm that does that in the software. There's a find closest points function, and it takes any two straight lines and it finds the 2 points that are where the lines pass closest to each other. And that's vitally important in fitting these points. But then it suddenly struck me, this was the light bulb moment. What if, having fitted the trajectory and corrected each point for gravity, what if we reapplied the find closest points algorithm? So for each separate point, we could recalculate, and those little green spots, instead of starting to drift downrange in the trajectory, they actually get to being the two closest approach points, which is what we want to see. And the further down you go, the more is the betterness of the closeness of the points. So that's what seems to be happening in a three-dimensional sense, just thinking about it. But then if we go inside the code itself, here's on the top magenta box, we're applying the find closest points algorithm to the observed point and the fitted point. and that gives us the vectors of the two closest approach points. Then we go down and apply the gravity drop. That's what's giving us our drift down range. So we reapply the find closest points algorithm, and that gives us the better results that we're seeing. Now, to just finally test this out, we were very lucky in January that there was a really, really nice long duration fireball over the north of Scotland, seen by 9 cameras. One of them was just into the north of England there at Kielder. And when we compare the two methods, here's the original gravity correction on the left, here's the new method on the right, all nicely built into the software. And as you can see, we're back down to the 0 line with the observed line of sight residuals. And also with the spatial residuals, there's the gravity splay with the original method, and with the new method built in, we see that despite all the randomness, it's managing to nicely hug the 0 line. And that's all I want to say, except to thank the GMN and UK Meteor Network camera operators for all your lovely data. Also, big shout out to Mark McIntyre and Radim Stano. I've pestered them mercilessly for data files, and they've been very obliging and bent over backwards to make sure I have all the ones that I needed. And also, of course, to Dennis Vida and colleagues, not just for developing the WMPL software, but for making it open source, and for the superb, I have to say, superb documentation, both in that paper, Dennis, and within the software itself. It's about the only software program that I've actually been able to follow that I didn't write myself. So thank you.
Thank you so much. That's incredible work, and I hope to see the correction implemented as soon as possible, because this is exactly how we imagined when we were starting this project, is that we're putting this out there, and there are some things and new things that people are going to find, bugs potentially, and this is incredible. Thank you so much. And we're definitely going to write this up as a paper or something, because it's actually significantly novel. Again, in the interest of time, I'm asking for Pete Eschman to start with his talk, and please put all of your questions in chat. There are going to be breakout rooms at the end, and that's about it. So yes, thank you so much, Jamie. And Pete Eschman, please go ahead. We can see your slides.
Okay.
It's all good.
Good. Let me see if I can get my window moved over so I can see all of our participants. There we go. Hello, my name is Peter Eschman. With lots of help from other volunteers, I've developed Pi RMS images for the last year or so. I started with OS system updates to the Buster image that Dennis created. Next, I developed a Bullseye RMS image with much help from Ed Harmon, who adapted the RMS install script in a forum message from Raoul Gouldman's. Milan Kalina assisted with changes to the Conti desktop display and removal of watchdog processors that were no longer needed. Others helped with beta testing. As recommended by Dennis, we changed the username from Pi to RMS. This helps guard against the barrage of bot programs looking to break in with username Pi on every device they can find. Once Bullseye was ready, Radim Stano updated our wiki links to point to newer images. These days, I'm working on developing the Bookworm RMS image with the help of Ed, Radim, and Milan. We have a few other people helping with beta test images. Before I continue, I want to make it clear that I'm not an expert in any of this stuff. Pi operating system names follow Debian, using character names from the Toy Story film series. Debian started this with the '96 release of Debian 1, codenamed Buzz. I've heard that Bookworm will be followed by Trixie and then Forky. Over recent RMS history, It begins with the Jessie release, which has been deprecated for a long time, but still needed for Pi 3. Jessie RMS uses end-of-life Python 2.7.9, which means that full camera control and machine learning event filtering are missing. Raspberry OS stretch followed Jessie, but I don't think there was an RMS image for stretch. After Jessie, Dennis developed the next release called Buster. Our Buster release was followed by Bullseye, and soon will be followed by Bookworm. So why all this recent image development? Our development cycle is driven by operating system releases from the Raspberry Pi organization. The organization only supports the latest and previous OS releases. Now that Bookworm's released, Buster will be deprecated, with operating system support ending in June. That's only 4 months from now. Bookworm is required for Pi 5 hardware. Fortunately for us, Bookworm is backwardly compatible with Pi 4. Before I continue, I need to say that I'm offering my own opinions today that other project developers may not agree with me. With Buster deprecated soon, does this mean we should upgrade to Bullseye or Bookworm? Well, yes and no. Yes for security and support going forward, but no if you don't want to fix what isn't broken yet. We've been running unsupported Jessie RMS on Pi 3 for quite some time. You can take that into consideration when thinking about running Buster after it's no longer supported. Does recently changed OS support mean you should upgrade to Bookworm instead of Bullseye? Probably yes. Go with the OS that'll be supported longer, but maybe no, considering it's not very difficult to upgrade later. Either way, it's a very good idea to prepare to upgrade, and I'll cover that in more detail later. Eventually, Trixie or Forky or something else will replace Bookworm, causing Bullseye to lose OS support. What fun for us. We are caught in the wheels of progress, and we just have to adapt as time goes by. This can be a concern for an organization relying on unpaid volunteers to support a worldwide Meteor camera system with the goal of no Meteor unobserved. What goals are important during image development? We should reduce support loads on our volunteers by recommending people use the most recent RMS image. We should limit the number of RMS images linked in our wiki. We still have to support Jessie on Pi 3, but we should try to avoid old hardware. Anyone who cannot afford a Pi 4 or 5 should be encouraged to repurpose an old PC using multicam Linux, which is a topic for another day. In fact, multicam Linux was covered in last year's GMN conference. Now that Pi 5 are shipping, we're likely to see more Pi 4 on the used market. We need to be forward-looking. As new operating system releases introduce new procedures, we should use them. Here's one example. We used to use ifconfig to check network status, but now we should say run IPA. Certainly, people are free to install any tools they want on their own systems, but when we help newcomers, we should tell them to run IP space A. We should not release new RMS images containing deprecated software. Many people who are new to GMN are also new to Raspberry Pi and Linux, and there's no point encouraging them to use deprecated methods. We should try to reduce our support load by encouraging the replacement of older hardware and software. Wherever possible, we should strive to improve functionality. Let's talk about the new Pi 5. What does it offer over the Pi 4? A much faster and more capable CPU with 2 times overall speed improvement, 2 to 3 times. And a CPU that contains cores that are 3 generations newer. The graphics processing unit is twice as fast. We get increased I/O bandwidth from updated USB and a new PCIe interface. We get an OEM active fan plus heatsink assembly available that attaches easily to the board. We get a power button, an onboard real-time clock, and a micro SD running about twice as fast. We get all these improvements with a price increase of only $5 US. But we also need a larger 5-amp power supply because they're a bit more power hungry, and the Pi 5 requires a new case. The biggest advantage is that we can run 4 Meteor cameras on a 4 gigabyte Pi 5. I have been running 4 IMX291 equipped with 4 lenses very nicely. The system finishes processing soon after the end of capture, taking only 20 minutes or so longer than a single camera. These benchmarks were run using Raspberry Pi diagnostics, which you can find on the accessories menu. The values highlighted in red indicate some impressive speed improvements. I won't read all of this now, but you can see the improved speed of the micro SD, the improved speed of USB over the micro SD, and what happens when you try the brand new PCIe interface, where things get even faster. What are the pros and cons of Bookworm OS Pro, which is required for the Pi 5 and for all of us going forward? On the Pro side, it's the newest Raspberry operating system. It still runs RMS with no problems on Pi 4, and we have newer networking tools. Like Bullseye, OS updates are indicated by an icon that appears on the taskbar. We can run the latest Python 3.11.2. We can run multiple cameras on Pi 5 with Bookworm. On the con side, it's the newest Raspberry OS, so is it buggy because it's new? It runs Wayland graphics, which kills most remote control software. However, Wayland can be canceled, reverting to X, and then our old remote control software works. It's likely that marketing demands will force remote control software to support Wayland soon, since it's been adopted by Ubuntu and others. We can overcome this limitation by using WaveVNC and Tiger VNC client for remote connections, with file copying in a Samba directory with read-write access. Along with OpenVPN, we can use these methods to access stations outside of our local network. Another drawback to consider, PCMan File Manager does not work using sudo, so you can't paste files outside of home RMS using the file manager. Like Bullseye 64-bit, copy and file and paste operations with the file manager may require opening a second window for them to work predictably. For instance, cut in one window and paste in the other. This can be inconvenient. Before updating your OS, you need to back up important files, including SSH keys, config, mask, and playpot. And you also need a new, fresh micro SD card on hand. Fortunately, we have a tool to assist with this. You start up a terminal session that puts you in source RMS, and then type scripts/rms_backup.sh. This will create a zip file containing these important files, placing the zip in your home directory, which is either home Pi or home RMS. You need to copy the zip file from the Pi and store it in a safe place. Be sure to run this backup from time to time to save your important files. This is a crucial step towards disaster recovery, even if you don't plan to update your RMS image soon. You'll also need a fresh 128 gig or larger micro SD card or an external USB 3 drive. So how about storage requirements? You can run multiple cameras on the Pi 5, so you might want to plan for more storage. You should consider a good quality SSD drive running from a USB 3 port. You'll probably want 256 gig for 2 cameras and 500 gig or larger for 4 cameras. These days, larger storage devices don't add much extra cost. This busy slide shows the multicam directory structure. We are working on the best way to run up to 4 cameras on the Pi 5. This means changes to RMS first run, so we can detect the Pi 5 and then branch to ask if you want to run more than 1 camera. If running a single camera, we'll proceed the same way we always have for a single camera. If you want to install more than 1 camera or want to install a second camera later, we'll use the design that's already in place for multicam Linux systems and convert the first and any additional cameras to the multicam design. Of course, anytime you plow new ground, you never know what kind of rocks you're going to hit. But we plan to have the new Bookworm RMS image ready to release very soon. When running multiple camera systems, it's best to wire them differently. The Pi 5 is only one Ethernet port. You can add additional Ethernet ports using USB to Ethernet adapters. However, a cleaner solution is to use the built-in port to connect the Pi 5 and cameras to a power over Ethernet switch, which is also connected to your local network. This configuration does not need Wi-Fi because the Pi 5 Ethernet port is used for all connections to cameras and the outside world. If you want to keep running Buster RMS, there are several steps you should consider to update and back up your system. RMS is updated when the station boots each morning, so that's taken care of. But it's also a good idea to keep your operating system and support files updated. To update, start a terminal session and type sudo apt update && sudo apt dist upgrade. The double ampersands change 2 commands together, so you can run them separately if you would like. If you see a message about packages which are no longer needed, you can run sudo apt auto remove and sudo apt clean. I mentioned RMS backup earlier. It's also a good idea to make a copy of your micro SD card using accessories SD card copy. Start by mounting a new card in a USB adapter. The new card should be the same size or larger than your current micro SD card. Plug the new card into a USB port. Be sure to specify the correct copy from and copy to devices so you do not overwrite your existing micro SD card. If you want to speed up the copy process, you can delete old capture file directories to reduce the amount of content that needs to be copied to a new card. This utility can also copy your micro SD to a more reliable USB 3 SSD drive, so you can migrate away from the micro SD card. Both Bookworm and Bullseye make it easy to transition to boot from an SSD drive on the USB port instead of the less reliable micro SD card. It's important that we all stay up to date with our GMN wiki because changes are made in the wiki quite frequently. Be sure to use new RMS images from the wiki links when you need to rebuild an old station or help someone build a new. Thanks for your time today, and I'll try to answer any questions or comments you may have.
Amazing work, Pete. Thank you so much. Yeah, just to reiterate, all software support and everything is done by volunteers, and their names are right here. Most people who try to keep up with the software changes and everything. We might have time for just one short question, if there is any. But Pete, if you don't mind, we just want to transition to Mike's slide. So if there are any questions, just someone speak up. And if not, Mike can start with his talk.
Sure, I can't quite share yet. So once you've turned that on, I will do this. There we go. One comment actually about what Pete was saying about Wayland and VNC and other remote sharing is that I've been using Rust Desk, which is an open project. I'm using it for a couple of months now. It functions pretty much the same as AnyDesk. I've set up my own virtual private server for it. If anybody wants to give it a try, they're more than welcome to contact me about it. But I use it now exclusively, and it's performed quite well. I think it's just rustdesk.com or .org or something. You can look into it if you're interested. So
great, thank you, Matt. Yeah, we see the slides. I think you can go ahead.
Perfect, and you can hear me okay there, is that right?
Yeah, it's perfect.
Okay, I'm just going to start my timer so that I know how long I've gone for. So as I mentioned earlier, I'm Mike. I work for the Meteor Physics group at Western. And prior to coming to Western in 2016, I worked in near-Earth objects building search telescopes in Calgary. And then I worked as a geophysicist in Norway for 10, 12 years, something like that. My current project work is related to space situational awareness, pretty much exclusively, where we're designing and building cameras based on, for LEO tracking based on RMS. So it's quite interesting. I'm sure that in coming meetings, you'll hear more about that. Research-wise, I'm focused at the moment on tracked meteor spectroscopy, which is another fascinating topic, but doesn't have a lot to do with what we're chatting about today. What I wanted to talk about were different properties and I guess the performance of sensors and modules that, well, mostly the sensors that we've looked at over the last 7 or 8 years. So to summarize, in case I go on too long here, RMS, we started back 2016 or 2015, whenever it was. We were working with analog cameras and USB screen grabbers. Typically, these were CCD-based cameras. They were using SuperHAD or SuperHAD 2 chips. Now, we still use these cameras in some of our systems, but this was quickly replaced with CMOS sensors from the XMOR series from Sony, the IMX225. That was one of the first ones we used. StarViz line developed quite quickly and upped the game with the introduction of the 291, which is something that we still use quite frequently with RMS. I think most people are using the 291. Now, over the last couple of years, more and more modules or sensors have been released, and some of them are highly sensitive, and their specs, at least on paper, put the IMX 291 to shame. And so I was curious, we were curious, what advantage there could be to using some of these new chips. So we've tested a number of cameras throughout the years, and I'm going to present some of those results here. So everybody should be familiar with the flight of a meteoroid, but it's just to say that at Western, we work pretty much exclusively in this domain here with our radar and with our optical systems. So from about 110 kilometers in altitude down to, fireball region down at 20 kilometers. So this is the region that we're interested in. The cameras that we run at Western go from the inexpensive Raspberry Pi systems that you see at the bottom there, up to a very expensive tracking system, which tracks meteors as they come through the atmosphere and resolves details and level of a few meters. And we see fragmentation for pretty much all of the meteor, most of the meteors that we see down to very, very small sizes. EMCCD cameras, we run a pair of those, which are fairly expensive cameras as well, but quite sensitive. Stellar limits of about 11. And I hope to show here that we're actually approaching that with some of the systems with the inexpensive IMX series cameras that we're running now. Just to give you an overview of the system performance, you don't need to know too much about what's over here, but in green, we have the RMS systems. And second column from the right, you can just see roughly the limit magnitude that we achieve with the different systems. What I'm suggesting from this talk is that with the latest sensors and 25 millimeter f1 lenses, we're able to get down pretty darn close, if not better than magnitude 11 stellar limit. So it's actually quite exciting for not a lot of money. First thing that we often think about are the lenses themselves. In terms of what is going to put the most light on the chip. We run a range of different focal lengths from 2.8 up to 25, actually 35 millimeters right now. 2.8s we don't really run, but I do have colleagues in Calgary that have a couple of these set up, but don't really recommend them. The standard, of course, is the 4 millimeter, 6 millimeter in place with a little bit of light pollution. We run quite a number of systems here for satellite tracking, the work that we're doing now with the 8 millimeter, and we're just adding a 25 millimeter set over the coming months. So just to give you an idea of the relative size of sensors and how they've progressed, at the bottom of the relative size sheet there, you can see the green is the 225 that we started out with. Most of the 4 millimeter and 6 millimeter cameras are using the 291, roughly the same size. 385 we started using 3 or 4 years ago for our all sky coverage multi-camera setup, 8 cameras. We called it the Hedgehog. See a picture of that in a second. And that lately we've replaced with the IMX 678, which is much, much more sensitive and much better quality. 347, which we'll talk about, is similar, but not quite as sensitive. The 585 that you'll come across, which is a fairly new release, is a larger format, 1/1.2 inch, with quite good sensitivity on paper, but on Sky, I'd say it's not as good as what I see with the 678. Camera sensors. So this is a list of some, at least, of what we've tested over the years. Starting out at the top here, the Watec 902, still using some of those based on HAD CCD. Can you see we progressed through to the bottom here, where we're now, at least I'm recommending for the larger format sensors, the IMX 678, and especially the monochrome. It's available now in a monochrome from at least one source. And hopefully soon we'll see the 585 come out in a monochrome version as well. But of course, this comes with extra cost. We are used to our modules costing, say, about $50 for 291. For the 678s, we're looking at about double that. If we want a monochrome version, it's about 180 or 200 US dollars. And then we have to ask, is it worth it for the purpose, for the use that we have in mind? This is what you'll find on Sony's website here, the current lineup of sensors in the color lineup and the monochrome lineup. Everything in red, those are things that we've tested recently. The light green ones are the StarViz 2, and my comment on that is that StarViz 2 really does make a difference, and I certainly do recommend going for those sensors if you can. On the monochrome side, the only thing I've tested is the 678 monochrome. The 585 is very, very difficult to find right now in the monochrome version, but hopefully within a couple of months we'll see that. But to produce it, it's probably going to take an order of 100 or more cameras, which is something we're probably unlikely to do in the near future from Western anyway. Modules, we often forget about the modules, the silicon chip, or system on chip, I should say, the SoC, but they differ greatly across the modules. And I just wanted to put this in your mind to really consider that. I highly recommend sticking with high silicon if you can. Goki is now making chips which are based on high silicon, if not identical chips. They own some of the IP now. I'm not sure exactly well, I've got some ideas why that's the case, but I would recommend either of those two. We've seen some people use other SoCs and haven't had great results. They've been difficult to work with. So I'll just put that out there. Now, since I've got 2 minutes left, I'll try to finish the last 2 minutes here with some examples of what we're seeing. And I'll go in order of chips. So this is an IMX 291 with 4 millimeter. This is just this week. It's from RASC, Royal Astronomical Society Canada, camera at the Wilson Cooley Observatory in Alberta. It's not too far from Calgary, so there is some light pollution. And I've tried to list here, just on the right-hand side, roughly what the limiting magnitude is here with this particular setup. And it's about 6. We see maybe 6, 6.5 with 291s at a dark site. So this is quite reasonable. You can see the Starlinks coming through here. This is a stack of everything. Moving on to the 307. 307 came out. It's quite inexpensive. You can find the modules for maybe about $30, I think now, maybe even less. On paper, they seem great. This is the same night. We see again the Starlinks. This is a darker site in rural Alberta. About 6.5 for this particular image is the limit. But I find that these chips do glitch out. You'll see glitches, whether it's a function of the SoC or whether it's the chip itself. I'm not quite sure, but I don't recommend these anymore. 347s, this is a setup of 8 cameras, and this is one of the ones that we're currently using for satellite tracking. You can see the same set of Starlinks coming through here, and with this setup with an 8mm, we're down to about 8.5 magnitude. We'd see with the 4mm, it would be about 6.5 to 7, just slightly better than what we were seeing previously. Now, what I'm going to show here a comparison of some different cameras, some of the newer ones. I think this is quite dramatic. Hopefully, you'll find it dramatic when you see it. But this is the 347 with 8mm, just zoomed in here. You can see I'm using SkyFit, and I've just picked a bunch of stars here. Just going to show the results here of the photometric solution, the astrometric solution. It's quite decent. Seeing down to about 8.5 stellar magnitude. We'll look at the monochrome version. I can just go back and you can just see already just in the background, there's quite a difference in what it looks like there. If I look at the solution this here, I'm seeing down to about 9. I only picked a few at 9th magnitude, but it certainly is at least a half a magnitude better with that monochrome version. We'll go on, we'll look at the IMX 585 with a 35mm lens. And you notice it's fairly washed out. The lens itself has some softness issues, but actually it is quite sharp when we look at one of the next images. We're seeing here down to something in the order of about magnitude 10. So this seems quite good. I mean, we're quite happy with that. This, again, is at 25 frames per second, so it's quite exciting. However, if we look at the monochrome 678, and I'm just going to go back and forth here, and there'll be a better image of this in a second, but you can already see that with the 678, we have much better detail in the background. It's not nearly as washed out, and the stars are quite sharp across the field. So that's quite exciting. With this, I'm getting about 10.5. I haven't picked down that deep here, but it's about 10.5, say 10.5 plus. So this gets quite interesting, I would say. When I do a little bit more work here, I'm down to about 11 by picking a few more stars that are deeper. This is going to show an inset of the 678 on top of the 585, and this is where you really see the difference between the versions. So this is the 678 monochrome on top of the same field of the 585 color, and hopefully you can see that difference there. You see these washed out areas here, which you might think, well, maybe there are stars there, but you can't obviously pick anything out. But bam, for example, I'll just put my mouse pointer close to this one here. You can faintly see it here in the 585 color, and it just jumps right out from with the mono, which we expect. We've gotten rid of the Bayer mask, and we are seeing to the pixel level. We're not doing that spatial filtering with the Bayer mask. So this is, for the work that we're doing right now, is really the holy grail. This allows us to get down to about magnitude 11 for the work that we're doing with a 25mm lens. I'm showing 35 here, but 25 is what we're using. Just a little bit of a teaser here. This is it's about an hour-long stack. Some satellite tracks here is what I was interested in. This is the 8mm 678 color. We can put the 585 35mm in, and right away you see a bunch of tracks pop up there that you hadn't noticed before. You see this rotator here, this rotating satellite, and once you bring in the 585, you have more or less a continuous streak there that you can detect and interpret. If we put the 678 monochrome in there, you see that it gets even better, as we would expect. This faint track here in the 585 pops right out. So this is exciting. Expect to see more of this in the future. And as I say, it's I think highly applicable to the faint meteor work that we're doing at Western. We're using it right now for the SSA work, but this now approaches the very expensive EMCCD systems in terms of limiting magnitude. there are some other factors that prevent us from swapping those out, $50,000 cameras out with a $1,000 camera, but we may just get there someday. One or two more slides here. This is a 6-hour stack of the 678 mono or 35 millimeter. And this illustrates one of the issues that we actually have found, or one of the problems that we've found for ourselves, is that we almost have too much data. So we're getting so many detections now, and we put 8 or 15 cameras on a system. It can be a challenge to keep up with the processing in the daylight hours. So this is something that we're currently working on, is to try to reduce the workload that we see. And again, this is all related to satellite work, but does carry over to the Meteor side of things as well. So a summary here, this just gives you an idea of some of the different chips or sensors that are available and the stellar magnitudes that you can expect, stellar limits. For meteors, we typically expect about 2 magnitudes brighter than that for the peak magnitude limit. So with the 678 monochrome, for example, or the 585 monochrome, we might be able to get down to 9th magnitude peak, 8.5 or 9th magnitude for, we'll say, close to completion for the observations that we're seeing. So it's exciting and evolving, and watch this space for sure. The winner is, in my mind, it really, really depends. It depends on your sky conditions and the lens that you're using, of course. It depends on your budget and on your goals. For us, my focus right now is on SSAs, so I really want to go as faint as I can, and cost is less of an object. For meteor work, I would say that the 291 is sufficient for the vast majority of applications, but I think we're seeing it being replaced by the 327, which has similar performance. And for a similar amount of money, just a little bit more, the 662 actually gets us a little bit deeper. Now, I didn't show any examples of that here. I'm testing that right now at the moment, and it would be my personal choice. And then the 662 monochrome, which is coming out if you have an extra $100 to put on a module, then that would be my choice for wide field. For the narrower field systems, though, definitely the 678, and better still, the 678 monochrome. So I've gone over. However, that is me. That is my summary. I'm happy to take any questions in the breakout when we have that. I hope this is helpful.
Amazing, Mike. Those are some very powerful graphics, and I think that made a lot of people think. Now, yeah, so as Mike said, he's going to take any questions in the breakout rooms. So just so you know how to get there, if you look down on the bottom bar, there should be a little icon saying breakout rooms. If you click on that, you're going to see a list. You might see unassigned first. You have to collapse that, and then you're going to see room 1, and then rooms named after certain talks. If you're interested to join a conversation in that room, you just kind of click join next to that room, and it's going to take you there with a limited number of people, and then you can chat. This is now our meal break. I will personally eat lunch now, so you have no obligations to be around until maybe about 12 minutes as we've gone over, but we do still have that little block for a meal. So thank you again, and see you in about 10-15 minutes.
the development. Oh, cool. The development in sensors, I think, has been quite amazing over the last few years, even. And I know you're doing a lot of work with ZWO cameras and the different sensors. And I'd be curious to know what your thoughts are on applicable or the best sensors that you've come across for affordable or attainable meteor work.
Right. So as far as that's concerned, we haven't really looked at that in the last few years. My focus has been on asteroid survey, and so we've got a customer with deep pockets, and we're buying the $6,200, $4,000 tech cooled stuff, and basically try to get as much sensitivity as possible out of there. What I'm curious about, though, is whether the 673 rivals the 6,200, which is not that's not the IMX number. I think that's the IMX 445.
Yeah.
I don't know if I got the number right. Whatever the ZWO 6,200 has in it, I think it's the 445. Yeah, but so that's kind of curious that the 678 may be an interesting alternative, but it's not as big a chip. So we're dealing with a 62 megapixel chip, and so that's they want area coverage. It's asteroid and space debris surveying, and so you want spatial coverage, and so you want the big chip.
What are your fields of view then that you work with?
Oh, we're typically dealing 2 by 3 degrees. We're seeing down to limiting magnitude around 19.5. These are tacked onto a RASA 11-inch f2.2 telescope. So we got 6 of them ganged together, essentially at each site, and so got a decent side field of view that we look for. Clearly not doing meteor studies.
Hi, Herbert. Nice to see you here.
Hello, Dennis.
Hi. I can hear you well. I think you can start sharing your screen.
Okay, let's see.
Yeah, in a few seconds, you can start. It is the start time. Yeah, I can see your slides.
Yeah, but maybe I should share my full screen. Sorry.
For sure.
Because otherwise, I guess. And now.
Yeah, looks good.
And now I should be able to. Like this.
Looks great. Yeah. We actually see the screen with your notes.
Right. Sorry.
Yeah.
Display settings, I guess. Duplicate like this. Seems better, right?
It looks great. Yep. I think you're good to go. Thank you.
Okay, thanks. Well, first of all, thank you for inviting me to this GMN conference. This is something completely different. It has nothing to do actually with meteors, but we've been involved with Dennis in solving an issue about this work. So Dennis kindly invited me to present this. So this will be something completely different. And well, the title of this talk is are the auroral emission lines polarized? And well, the answer is yes, but the question is, what can we do for it with it? This is here my collaborators involved in this project, also from Grenoble in France. So what I will basically do first, I will briefly talk you about the auroral emission lines and their origin, because of course, not everybody here is a specialist in this field. Then I will briefly talk about the polarization of this auroral emission line by first telling you what actually we mean by polarization of light. And I will briefly give you some context and the theory for the polarization of the red auroral emission line at 600 nanometer. Then I will describe our observations and instrumentations with 2 different types of instruments, the so-called CRU instruments were developed actually in Grenoble. And then our latest instrument called PLIP for Polar Lights Imaging Parameter that has been mostly developed in my institute in Brussels. And then I will eventually show you why GMN was important and was helping us with the PLIP, with the analysis of the PLIP data. So just a little bit of context, the magnetic environment around the Earth's magnetosphere is actually perturbed, if I may say, or constantly interacting with the solar wind emanating from the sun, which has I don't go into all the details, of course, but that means that the magnetic field lines on the day side here are actually stretched towards Earth, while actually compressed towards Earth, while actually the magnetic field line behind the Earth are stretched towards the end of the magnetosphere. And in particular, at high latitudes, these magnetic field lines recombine in the equatorial plane in a region called the plasma sheet. And actually what happens is that when the magnetosphere is perturbed by the solar wind, or for example by a coronal mass ejection emanating from the sun, electrons from this region of the magnetosphere are accelerated along magnetic field lines towards the ionosphere. So this is what we usually call the magnetosphere-ionosphere coupling. And when these electrons are accelerated to really high speed, they hit the oxygen atoms in the ionosphere and excite them. And the de-excitation of these atoms actually produce the beautiful red and green colors that you can see. The red line is emitted at 630 nanometers at an altitude of about 220 kilometers, while the red is emitted at 110 kilometers. When you have really very energetic electrons, they can go deeper into the atmosphere, so below typically 100 kilometers altitude, and then they can excite also the first negative band of the N2 plus component at typically 427.8 nanometers. So this is what we call the blue line. Now, this is a picture that a photographer, Olivier Grunewald, took 2 weeks ago when we were in Norway, in Skibotn. Of course, this is a picture taken with a camera, but this is typically to show you the beautiful green and red display that you can see. The red is very difficult to see by eye, but the green is, of course, much more easy to see. All these oral display actually occurs in the so-called auroral oval that you can see here, and the position of this oval is centered on the geomagnetic of the magnetic pole actually. And its extent in latitude really depends on the geomagnetic conditions. During a really strong geomagnetic storm, usually associated with a coronal mass event, coronal mass ejections, the oval can extend to lower latitude. Actually, you can then see aurora in the south of France, for example, or in New Mexico, even I think in US. But this is, of course, quite rare event. Now, what we have been done actually for many years now is trying to study the polarization of these auroral emission lines. And by polarization, I briefly remind you here that we are talking about the vibration of the electric field in a plane that is actually perpendicular to the direction of propagation of the light. So if we look at this perpendicular plane, if the vibration of the electric field stays in one preferred direction, we say that the polarization is linear. If it rotates in one direction or the other, this is in a circular way, the polarization is circular. In the most general cases, it can be elliptical. Usually, the polarization is characterized by the degree of linear polarization, which basically tells you how much of the incoming light is polarized. It's 100% if the light is fully polarized, and it's a small fraction otherwise. And the angle of linear polarization is illustrated here or there. It's the angle between preferred direction and the direction of the polarization. So of the electric field, sorry. What is important when you study the polarization is that the polarization that you observed in the radiations contains informations either about the source of the radiation, which produce some polarized light, or most of the time about the objects or processes that interacted with the radiation and created this polarization. And usually it's associated with something that is when there is a preferred direction. So this is the case, for example, with scattering, but this is also the case with magnetic field. And so what can create the polarization of auroral emission lines? There is this preferred direction because the electrons are precipitating along magnetic field lines. Of course, they are not exactly aligned, and there are some, what we say, pitch angles, so direction between the angle between the direction of the electrons and the direction of the magnetic field, but there is still a preferred directions. And when these electrons impact the atoms and molecules of the upper atmosphere, they can then give rise to linear polarization. So that's the simple explanation. Now, of course, if you look at details, in this particular case of impact polarization, this is a quantum mechanic effect. And I will, of course, not go into the details because I'm not a specialist myself. But in this case, the polarization results from a differential Zeeman sublevel. So the Zeeman sublevels of a line are due to the presence of the magnetic field lines in this case. And so for the green and the red line, which are produced by de-excitation of oxygen atoms, they are illustrated here. For the green line, the upper level of the transition has a total kinetic momentum equal to 0. Therefore, there is no Zeeman sublevels possible in this case. Hence, there should be no polarization for the green line. For the red line, it's a different story because the upper level has G equal to 2, and therefore there are 5 Zeeman sublevels, and the impact polarization is possible. But for a long time, because this red line is a forbidden transition line with an extremely long lifetime of 110 seconds. And for a long time, polarization was not expected because collisions with atoms and molecules or any other item actually would destroy this polarization because collisions are more homogeneous. So it was not actually looked at, but actually because the red line emission is at 220 kilometers, the collisions are much more rarer there, and therefore it was still worth investigating. Something that the group of Grenoble started around 2010 with the group from Jean Linenstein. There was also some theoretical work done by Véronique Baumier. Again, it's quantum mechanics. I will not go into the details, but what is interesting, she did the theory for one electron impacting a single oxygen atom. And what she found was that the degree of polarization was typically around, well, could be up to 17%. And very important that the polarization should be aligned with the magnetic field line. But of course, this is just for one electron and one oxygen atom. Now let's talk about observations. These observations, we had to go inside the oval, of course, and we had for quite some time now a collaboration with the University of Tromsø, which has access to this Skibotn Observatory in Norway, about 2 hours drive from Tromsø, which is the main city up there. So basically we go inside this dome and we observe from there. We put our instruments there. I briefly show here that actually there are also Meteor cameras that you can see in the red circles. These are Meteor cameras from UA Virinen actually. The first instrument sorry. The first instrumentation that we use were actually, as I said, developed at IPAC in Grenoble, and we call them the line of cru. You see them here, the three of them, Corbel cru, Grand cru, and Petit cru, in a nice picture that was taken by some colleagues from Grenoble. Okay. Doesn't move anymore. Okay. The principle of this instrument is sketched here. So they use a very sensitive photomultiplier with some lenses, but they also insert a narrow interference filter. In this case, the red filters centered at 630 nanometer. And in front of the instrument, you have a rotating polarizing filter, and the field of view is of 2 degrees. So this rotating polarizing filter makes, when it turns from 0 to 360 degrees here, you see the intensity of the light will actually follow a kind of this curve, which is actually the malus law, with 2 maxima and 2 minima, if the light is polarized. If the light is strongly polarized, then the difference between the maxima and the minima will be higher. If it's not polarized, then you will basically measure something that is flat. And the position of the maximum gives you the angle of polarization. So this is basically how you measure polarization with this type of instruments. And this was used for a few years, actually. This is some results for the red line. Here you see the intensity of the line, the degree. Sorry, my mouse is going everywhere. So this is the degree of linear polarization and the angle of linear polarization. And one thing, I will not describe all these results because I could talk for a very long time, but one thing that I would like to mention is that the degree of polarization that you see here is just of a few percent, not 17% like the theory predicted, but this could be explained very easily because you don't have one electron, but distribution of electrons with different pitch angles. And when you take that into account, plus other mechanisms that can produce the red emission lines, but not by impact, by other more isotropic phenomena, then you can explain these values that are much lower than the theoretical ones. On the other hand, you see that the angle of polarization is more or less centered around 0 degree, which in this case was the direction of the magnetic field line. So it was somehow making sense. Now, of course, we were all interested in other lines, and in particular the blue line. Why? Because it's still the third most intense auroral emission line. As I said, it's also produced below 100 kilometer altitude, so by a different population of electrons, much more energetic. So these observations would be complementary with those from the red line. And also the blue line is created only by impact with electrons. So in principle, we could have expected a larger polarization, although there is actually no theory for impact polarization for this line, this band actually. This is an example of the results that was obtained with one of the CRU instruments. One of the things that is a little bit striking is that the polarization level is relatively low, so that has to be explained. But I will not go into more details here. What was very surprising with this instrument, so all this work were actually done by Leo Boss, my collaborator, during his thesis in Grenoble. And they actually looked also at the green line, and they realized they were expecting 0 because, as I mentioned in the theory, it should not be polarized. But actually, they were very surprised that it was also polarized. Then you can say, what is the origin of this polarization? It's still something we are searching for at the moment. One of the things is it's not an artifact because, well, first, if you look at this data, you see here a very smooth rotation of the angle of polarization, something that cannot be due to an artifact. And it's more actually reminiscent of the interaction of two mechanisms that would produce polarization. And of course, this was also checked with how it varies with geomagnetic activity, something that cannot be explained, of course, by an artifact. So there were many, many reasons now to convince us that it's real, but the origin of this polarization is still debated. So one thing we had in mind was to build a different instrument, an imaging polarimeter that we call PLIP, for polar lights imaging polarimeter. This original idea actually was a few years before, when we discussed with Franz Nick from University of Leiden, and I think I saw Felix also attending this meeting. Felix came with Franz and the group with the very first preliminary design of these instruments like 6-7 years ago at the Sheboygan Observatory. But this is what we have done in the last 3-4 years. We have developed this instrumentation using 4 identical. So the difference is that now we are using 4 identical commercial ZWO camera with very low noise for deep astronomy, actually. So you see them here all aligned. And the difference with the previous instrument is that the polarizer in front of the 4 cameras are fixed, but oriented at 4 different angles. And by combining these images 2 by 2, we are able to compute the Stokes parameter from which the degree of polarization and the angle of polarization are calculated using this classical formula. So it's a different approach, of course, compared to the CRU instrumentation. It's a different way of measuring the polarization, but of course we should find the same thing. But the important thing is that we have a large field of view with these cameras, and also we are able to measure the polarization in the green, blue, and red emission lines as well. As I mentioned, these instruments are complementary because the CRU instrument, they have a small field of view, 2 degrees. The other one has a really large one. And the CRU instrument has basically 1 pixel. So no space resolution at all, while the other one has many pixels for PLIP. And therefore, we can study how these polarization parameters vary across the sky. CRU is also extremely sensitive. It's a PM. And therefore, it can have a much better time resolution than PLIP. So the instruments are actually complementary, but comparing the results from the two is not that easy because we have to degrade the time, space resolution of PLIP, or degrade the time resolution of the CRU. Here you have a sketch of inside the dome where you see the 4 cameras from PLIP here attached 2 by 2. And on this side, you can see or guess that one of the CRU instrument, Corbel CRU, is attached to the same astronomical mount. Now, finally, where did GMN help PLIP? This is an example of 4 images taken by the PLIP instruments with the green filter. So you see in this case a faint diffuse aurora on the left-hand side. But the difficulties, of course, was that we had to perfectly realign these 4 images. And my colleague were using simple tools to try to do that and produce some results. But the thing is, we realized that the alignment of the 4 images had to be done to the subpixel level. And was that possible? They had no experience, but I knew by the GMN network that Dennis had developed, and Dennis and maybe others have developed these tools actually for the GMN network. So we got in contact with Dennis, which introduced my colleague to the SkyFit program. And now they are able to perfectly realign the 4 images using the precise astrometry that we can do with SkyFit. Because now, of course, we are modeling also the distortions of the images introduced by the lenses, something that my colleagues were not doing before. And so we can actually now check this with individual stars. That's actually one of the difficulty for the green images, because in this one is fine because you see a lot of stars. But of course, when the aurora is really bright, we have to find enough stars to be able to apply this astrometry. But so far, so good, apparently. This is one example of results that we had with Blip before actually using this realignment using SkyFit. And okay, we still see interesting things, of course, for the DOLP and DOLP. So here you have a really nice auroral arc, very bright. And you see that in the degree of linear polarization, we see a little bit of decrease. I did not talk about that, but that's something we see a lot. So that makes sense. But what was mostly interesting here is that the angle of polarization, you see a clear rotations in the arc. And that's something we definitely want to study in more detail. One of the things that was strange in this result was that the DOLP seemed to be maximum on the edge of the arc and with very large value compared to what the CRU instrument were measuring. And actually we were able to simulate that it was due to a misalignment of the images by 1 or 2 pixels. It's enough to create a really strong polarization. Now hopefully this will not be the case anymore for these artifacts. Okay, this is still work going on, and I try to summarize here what we have done. So, well, first, it's very complex topic because the more observations we do, the more difficult behavior we see, both so in terms of measurements, but also in terms of physical interpretation. One of the things we believe is that the measure of the angle of polarization of these auroral emission lines on a large scale, so typically on the field of view that Blip sees, might be used as an indicator of the direction of ionospheric currents. So yeah, there was a sketch that I showed, but I didn't go into the details. When you have these electrons precipitating, there is really an auroral electric circuit. So there are currents flowing into the ionosphere and closing the currents going upward and downward. And therefore, being able to see these currents would be something, if we can relate them to the direction of the angle of polarization, that would be something really fantastic. And this is one of the main goals, I would say, of Blip. And later on, the idea would be to use these data as proxy also to include in space weather models and include them, try to improve these models. And as I mentioned, with the help of Dennis, now we are able to properly realign the 4 images obtained by Blip. So the idea is that in the future, we will be able to analyze a lot of data. The investigation is still going on, and we have now planned with the University of Tromsø to install Blip permanently at the Sheboton Observatory to collect more data remotely, because campaign observation, as we have done, really depends on the weather, really depends on the activity itself. And even if we go 1 week or 10 days on site, there's never any certainty of getting good observations. So in the end now, the instrument is sufficiently mature to be piloted and controlled remotely. And that's what we plan to do this year. And I have no idea how long I've been, but sorry if I've been too long.
No worries. Thank you so much. It was an amazing talk. Very interesting stuff. We are a bit over time, so we're gonna switch to the next talk. The next talk is actually quite short, less than 5 minutes. So we're gonna be done with that quick. And I opened a breakout room, so in the next break, everyone can just go in the breakout room, ask any questions, and of course, put questions in the chat as well. Thank you so much, Hervé. And the next thing I'm gonna do is I'm going to share my screen, and I'm gonna play you a pre-recorded talk by Radim. Just give me a quick second here. I think I have to share my sound here and open here. And
we manage also.
Oh, here it is.
Good evening. My name is Radim Stano, and welcome to the presentation about Global Meteor Network Outreach Project. Unfortunately, I can't be with you online tonight. I have pre-recorded this video. I was talking about Global Meteor Network Outreach Project a year ago, and now let's have a look where we stand after 1 year. First, let me remind you what is this project all about. It's a STEAM project for high school students, so it's science, technology, engineering, arts and mathematics. Students will assembly, mount and operate a camera or get a plug-and-play version. They will learn about astronomy, RMS and computer science. It is module-based. We have prepared tasks, games and competitions for them. There will be also a big closure students meeting at the end. We started to think about this project and how to create an outreach project for students around our Meteor cameras in 2022, and we started to shaping it shortly afterwards. Status after 1 year. First schools onboarded this project in September 2023, but we learned that not all schools all over the world start their school years in September, but in Southern Hemisphere rather in January. We have 10 schools on board and one summer camp concluded this project in the summer of 2023. We handed over 18 cameras, of which 9 were built from scratch, 8 plug-and-play versions, and 1 is to be handed over. We have schools in 5 countries, and we hope to have schools in Western Australia onboarded this project soon. Where are our students located? Summer camp is located in Washington State in the USA. Then in Europe we have 3 countries: Germany, Austria and the UK. In the UK it's Wales and Scotland. In Wales it's Montgomery Church in Wales Primary School, St Mary's RC Primary School, and in Scotland Inverclyde Academy, Peebles High School and Wick High School in the north. In the North Germany, it's Friedrich Schiller Gymnasium, Preetz, in the south of Germany, Gymnasium Untergriesbach, and in Austria, Bundesrealgymnasium Kepler in Graz. In South Africa, we have primary school in Touws-Rivier and high school in Laingsburg. We hope to have schools from Western Australia on board very soon. This will be in cooperation with Perth Observatory, and Lexi and David will tell you about their amazing outreach project they conducted recently in the session 2. We also prepared some materials, and on some we are still working. The most important and the first published material is task games and competitions. There are 12 of them inside. Astronomy module is close to be published, and it will be worth waiting. It's got more than 100 pages already. Computer science module and RMS module are still in preparation. All these documents are or will be publicly available at our website. But there are still some things we need to finish. We need to ensure that all installations are done and cameras are operational. We need to finish all the materials and publish them. We need to create a guide for the teachers, and we need to work with schools and establish partnership with them for the future. We need to do the evaluation after the first run, and we need to onboard Western Australian schools in cooperation with Perth Observatory. None of this would be possible without our team of volunteers. Let me introduce them. Mary McIntyre, Mirjana Malaric, Laurie Stanton, Tim Cooper, Rob Steele, Paul Rocher, Horst Meyer-Dirks, Dennis Vida, and me. You can find more information about us on our webpage. We managed also to create a webpage, and you can find all the information about the project, all the materials, our team, and you can contact us through this webpage. Its URL is globalmeteornetwork.org/outreach, and it's linked also from our main webpage. All the news about projects progress are also posted here. Last but not least, let me thank to an anonymous donor who sponsored cameras for this project, to the Astronomical Society of Edinburgh for sponsoring 3 more cameras, and to our team for the great job they are doing on this project. Thank you for your attention.
There we go. That was the talk by Radim. As you can see, the outreach program is well underway, and hopefully we can get more schools. And when we publish the materials, maybe one day that can be compiled in a book. But everything is planned to be kept open source and free, so all teachers can use this, build cameras, and deploy and introduce more kids in science. Okay, so next one, we have, we're a bit late, but we do have a talk from Oriana Gall, an invited talk. She's gonna tell us about how we predict meteor shower activity. Oriana, are you there?
Yes, I'm here. I'm just trying to share my screen. Can you hear me well?
Yeah, I can hear you just well. Yeah, go ahead. I can see the screen and I think you're good to go. Thank you.
Thank you. So this is actually a talk based on a review talk I gave at ACM last June. So just in case some of you want to take a longer break, but without with Dennis, that it might interest the GMN community as well. I'm a bit sick today. I hope that won't disturb you. But today I would like to talk about comets and what meteor stream modeling can teach us about comets. So comets are really the building blocks of the outer solar system, or better say they're the leftovers of the solar system formation. They're very primitive bodies that still retain the traces of the chemical and physical processes that were at play at the early stages of the solar system formation. And although they form quite far from the sun, many periodic comets travel within the inner solar system, and this allowed several spacecraft to visit them since 1985, like the Giotto spacecraft or the Deep Impact, or more recently the Rosetta space mission that went to visit Comet 67P. And these missions are really important because they help us understanding the nature and the structure of these bodies. But they also have their limitations. They are only able to visit a few targets that are not too far from the Earth. And since the first space mission launched to a comet in 1985, about only 1.7% of the known periodic comets have been visited by a space mission. Luckily, comets leave behind billions of small messengers that can inform us about their past behavior. Those are the meteorites. When a comet approaches the sun, it will partially melt and eject lots of dust into space. These meteorites are released from the surface of the comet with a non-zero ejection velocity, which will induce a change in their orbital period. So that's why you see the dust trail that will start stretching along the comet orbit. And each time the Earth enters into one of these dust trails or meteorite streams, we see a meteor shower. And we see actually plenty of meteor showers on Earth every year. I would like to have meteor showers every day. Yeah, currently in the International Astronomical Union Meteor Data Center, we have about 112 established meteor showers and more than 800 candidates in the working list. So when we think about it, the Earth is sampling material from tens of different parent bodies every year. And we even regularly examine twice as many comets as space missions do, but without like, sorry. So we're sampling this material from all these parent bodies, but we're not here only looking at the short period comets. We're also looking at asteroids or long period comets. So comets that have a period above larger than 200 years, they're actually very hard to observe. And what's interesting here is that most of the meteorites that produce a meteor on Earth today were ejected from their parent comet a long time ago, sometimes centuries or even millennia ago. So the meteor showers actually give us information about the parent bodies long before the era of telescopic observations. So currently, about 90% of the meteor showers we observe on Earth come from comets. And the question is, how can we use this connection to learn more about the history of this comet? So we're going to need two things here. The first one is long-term consistent meteor observations. I'm going to talk about those a bit later. And the second one is a realistic stream model. So how do we perform a stream model? The first connection between the comets and the meteors was established by Kirkwood and Schiaparelli at the end of the 19th century, and this sparked the beginning of stream models based only on the motion of the parent body. And the idea was to say we expect a meteor shower to occur when a comet will cross the ecliptic plane close to the planet. So when its normal crossing location will be near the Earth. And this allowed predicting the time of some meteor showers and storms in the past, especially young showers that were not very perturbed, but it also significantly failed in predicting other more complex meteor showers. And this is because the meteorites do not evolve like their parent body in space. Dust trails disperse over time, and they're also influenced by radiative forces or planetary perturbations. And I like to show this animation developed by Rachel Soja that shows how the gravitational perturbations from Jupiter can really disrupt the stream ejected by a comet 67P. So we see that planetary perturbations can really complexify the stream structure, creating gaps and regions of higher density. And for these very perturbed trails, after a few revolutions, it becomes really hard to link the meteorites to the parent body. So that's where numerical simulations came into play, because with full dynamical models of meteor streams, you can include all these tricky orbital effects very easily and for a high number of particles. And with the development of the computing power, the numerical simulations of streams became the predominant approach in meteor showers prediction. So how do we model numerically a meteor stream? The idea is to eject meteorites from the parent body sometime in the past, to integrate them up to the present epoch, and then to compare that with meteor observations. So this is just an example of a stream we modeled from Comet Encke. So the first thing we needed to do is to determine the ephemeris of the comet, sometimes over long periods of time. Here we're talking about 32,000 years. We know that this is complicated, especially for perturbed outgassing comets. But then at each apparition of the comet, we're going to release particles. So a new dust trail. Here in the simulation, the different dust trails are color-coded by age. And we're going to integrate these particles up to the present. Then we need to select which of these simulated particles will produce a meteor on Earth, because we can't possibly simulate as many particles as the real number of meteorites that will be ejected by a comet. And even in these simulations, I have like, I think 6 million particles. Even with this high number of particles simulated, we only have a few of them that are actually going to collide with the planet. So we need to be a bit more generous in our selection criteria. And generally, we define a region around the Earth of a few hundreds of astronomical units. And we say, okay, all the particles that are within that region would produce an observable meteor on Earth. Once we select our meteor-producing particles, we then need to translate our simulations into parameters we can compare with the observations. So typically, we're going to model a meteor shower, not only the timing and the radiant, but also a full activity profile for the shower. So when we develop this meteor stream, the first stage is really to build an hypothetical story for the parent body, for the comet. So where was it located, how active it was, how did it eject particles, more large particles, small particles, which density. And these selections, these choices are usually rely on the observations we have from the parent body. But sometimes we don't have enough observations to have the answer to all these questions. Then we need to make additional simulation choices. Do we have enough computing power to simulate millions of particles? Are we ejecting particles at each apparition of the comet? Are we including non-gravitational forces? How are we handling planetary perturbations? And then, as I said, we need to establish subjective criteria to determine which particle is going to produce a meteor on Earth, and what distance or time are we considering to select these particles, and how are we going to calibrate our simulations to produce realistic activity profiles for the shower. And that's why you see, when you establish the model, you really need to take into account a bunch of parameters, and many of them are the best guess you can apply to your model, and that's why meteor showers are really important, because they're our only way to calibrate our simulations and to validate the stream models we're developing. So how do we use these meteor observations? The first step is a bit stupid to say, but I think it's important. We need the meteor observations to identify the parent body, and we can't develop an accurate stream model if we don't know the parent body. And this, might sound stupid, but actually it's a complicated task to link a shower to the parent body. In the current list of established meteor showers, only 16% of them have been successfully linked to an asteroid or a comet, and that's due to several reasons. Some of these parent bodies are very perturbed, others disappeared, other ones are the parents of multiple meteor showers. And so we stand with the development of meteor showers observations and increasing number of near-Earth objects that we discovered. More and more linkages between streams and parent bodies have been proposed. But these linkages are essentially based on orbital similarity criteria, and has been shown by Ponzier, for example, that only about a fourth of these proposed associations are statistically significant. So we need the meteor observations to identify the parent body, but then we need to develop a full stream model of this parent body, of the meteorites ejected by this body, to see if we can reproduce the observations. And this is how we're going to confirm the parent body and stream link that we established. Then, of course, we use meteor observations to have information about the meteorite's structure, composition. We now have spectra of meteors, like this beautiful spectra of a fireball that was captured by the European Fireball Network. We also have detailed models of the fragmentation of the meteorites in the atmosphere. Here, the animation shows one of a record from the Canadian Automated Meteor Observatory, where you see a small meteorite fragmenting in the atmosphere. And all these data give us estimates of the meteorite mass, strength, density, and composition that we can feed directly into our model. And then finally, last but not least, what's really important to constrain the stream models we develop is to have a good track of a meteor shower's activity. Not only the radiant and the timing, but also of its activity profiles, and preferentially over long periods of time. And that's why I'm super excited to see that now GMN compute fluxes for all the shower it observes. I think that's really amazing. And of course, we want to have like as much data as we can over time for a meteor shower, and that requires wide detection network. But luckily, detection networks like GMN or CHEMS or Fripon, YFN, DFN, and many other ones are actually turning the Earth into a giant meteor detector. And they're feeding the databases with thousands of orbits and a very good tracking of the shower activity. So that's really great. In addition to these video cameras and these networks of visual observers, we also have dedicated instruments. In the radio range, we have professional radars like SAMR or Seymour in Canada that are also able to monitor the shower's activity, compute the orbits, and are able to see meteors that are too small to be recorded by optical devices. So using all these complementary observations of a meteor shower, we're able to probe different size range of the meteorites and have all the data that we need to constrain our simulated meteor shower model. So now we have all the observations and all the model. What can we learn about the parent? We talk about the parent shower association, but then the natural outcome of that is also to know that we have right ephemeris for the parent. If you're ejecting particles at the wrong place in the solar system in the past, there's little chance that you're going to produce the right meteor shower at the right time on Earth in the future. And a good example to illustrate how the models can constrain the ephemeris of the parent body is the case of the Taurid complex. So the Taurid is a broad, massive stream of meteorites in the inner solar system that produces at least 4 major meteor showers on Earth: the northern and southern Taurids, the beta Taurids, and the zeta Perseids, as well as several minor showers. So all cumulated, the activity of the Taurids is lasts for several months every year. And in addition, the complex is responsible for enhanced variable activity due to a swarm of resonant meteorites. And we know that we have like these large bodies, like tens of meters or hundreds of meters size NEAs in the stream as well. So in 1940, comet Encke was proposed to be the parent body of the Taurid complex, but the comet has often been judged too small and its activity too low to explain by itself the full mass of the complex. And that's why several authors, Klub, Napier, Asher, proposed that Encke is actually the largest member of a broad Taurid complex that was formed by the fragmentation of a giant comet 20 or 30,000 years ago. So we perform a new numerical model of the Taurid complex to investigate this question and see if Encke could be the main source of the Taurid complex. So we modeled the meteorites ejected from Encke over the past 30,000 years. This is the animation you saw before. And we compared with 2 decades of meteor observation using different size ranges from visual to radio range. And here on the left, what you see is how the normal crossing locations of our simulated particles in color compare with the observed orbits of the showers associated with the Taurid complex. And they were in quite good agreement, so we were happy, and we started looking at the radiance. And again, the simulated radiance here in color matched really well the observed radiance, all these dark symbols you can see here. So then we look at the timing. And we're really disappointed to see that we're doing a very bad job in modeling the timing of this shower. What you see here, like these kind of blurred regions, are the observed average activity of the 4 major Taurid showers observed by Seymour. And these solid lines here represent our model. And we're able to reproduce the time or the duration or even the intensity of any of the Taurid showers. So that's why when we develop a stream model, it's really important to compare the output with all of the observations we have, and not only to look at roughly the time and the radiance that were correct in this case, but realize that we weren't able to reproduce the activity of the shower at all. So we decided to try again to develop a new model. And in the end, we tried again 115 times. We explored more than 100 stream formation scenarios from Encke simply by slightly changing the ephemeris of the comet, always remaining within plausible values for the comet. And other scenarios explore more these giant breakup hypothesis that Napier proposed. And in the end, this is just a summary. We found one scenario that was actually able to reproduce all the observed characteristics of the 4 major Taurid showers. So the radiance, the timing, the intensity ratio, the timing, and the duration. So that means that with this specific dynamical history that was obtained just by slightly twisting Encke's orbit, we are able to reproduce the major characteristics of the Taurid complex. And so that maybe Encke is the sole parent body of these major showers. And that's interesting because there's still some mystery about how Encke arrived on its present-day orbit. We're not able, Encke is a weird comet. It's the only member of its own class, the Encke class comet. And we still don't know exactly how it arrived where it is today, while still showing some signs of activity. So maybe our constrained ephemeris, so the ephemeris we developed constrained by meteor observations, will help unveiling the origin of this mysterious comet. Stream models can also help you constraining the activity of the parent body. And to illustrate that, we can talk about Comet Halley. Comet Halley produces 2 annual meteor showers on Earth, the Eta Aquarids in early May and the Orionids in late October. And both showers share similar characteristics. They last for about a month, and they have average maximum ZHR of 2040 for the Orionids to 70 for the Eta Aquarids. But the 2 showers are known to display occasional outbursts that are caused by particles trapped in mid-motion resonance with Jupiter, meteorites trapped in mid-motion resonances with Jupiter. And we wanted to develop a new model of the halides to try to predict when these outbursts could occur and what's the intensity of these future outbursts. Because in particular, these showers are also quite dangerous from satellite safety perspective. So we developed a new model of the halides. We generated, I don't know, like 5 million particles over 5 and 7,000 years. And we tried to reproduce the characteristics of the Orionids and the Edda-Quaritz with a single model. Here I'm just gonna show the results we have for the Edda-Quaritz. But the important thing we found about this model is that we were lucky to have 35 years of meteor observations to calibrate our simulations. So 35 years of Orionids and Edda-Quaritz observations in the visual, video, and radio range. And I think this allows us to develop the best constrained shower model to date. So thanks to this large amount and very accurate meteor data, we were able to reproduce all the past apparitions of the Edda-Quaritz meteor showers. So the global shape, intensity, duration, and also we were able to reproduce the average shape of the activity profile. What you can see here, all the simulations results, sorry, are given here in red, and all the observations are drawn with other colors. So our model allowed us to fix an age for the shower to 5,000 years. And for the first time, we're also able to model a realistic mass distribution for a meteor shower. We found the visual size index to be of 1.84 in our simulation, which is actually quite close to the value reported in the literature of 1.87. And our model also showed the strong dependency of the mass index with the mass range you're looking at for the computation. And this can explain the discrepancy of the mass indices given in the literature for the two showers. Our model also performed quite well in predicting the maximum activity to be expected for the shower every year. So you see here how the simulations in red compare with the observations for the different years. And we're able to find this maximum value within an uncertainty of 20 or 30 meters per hour. So this gives us confidence to forecast the shower activity until 2050. We released the paper in 2020 here where the black line is. And so far until 2023, the forecast still holds. The model is still valid. In particular, we predicted an outburst rich in small particles in 2023, something that wasn't really shared by the other modelers. So I was very nervous about that. But it appears that the outburst was successfully reported by the Seymour radar. Here you see how the observations compare with the predicted meteor shower in 2023. The predictions are in blue. The outburst wasn't reported by GMN, but because it was really rich in small particles that couldn't be observed with the video cameras, and it also occurred during the full moon. So that's why the video cameras missed most of the outbursts. So we developed this successful model of the halide stream. And this example illustrates how a good model combined with long-term consistent meteor observations can actually constrain the history of a parent body, in this case, during more than 5,000 years. So that's pretty exciting. And please note that we have predicted another outburst in 2024, so next May. So yeah, we'll see if we still have the same conclusions in a few months. But you should definitely observe it because we're expecting the outburst to be rich in larger particles, so more variables that should be very well detected by GMN. The stream models can also help you constrain the ejection processes at the comet, and I'm going to go quite quick with that and just show the example of Comet 73P Washman 3, because we know that this is a very famous comet. It disintegrated in 1995. We have this major outburst. It broke in at least 4 pieces that kept disintegrating over time. And the comet is associated with the Thor Hercules meteor shower. But apart from a controversial outburst in 1930, the shower displayed little to no meteor activity every year. But the question was, we know that this comet released a lot of dust into space in 1995. So can was the comet able to produce an enhanced meteor activity at Earth in 2022? So a few modelers work on that. They propose different scenario, and we realized that when we're ejecting the dust from the comet at typical gas drag speeds, the meteorites were completely missing the Earth in 2022, so nothing could be observed. But if you were ejecting the particles from the comet with a higher ejection velocity, then we could have like an enhanced activity in 2022 or even a storm. So it was hard to decide between these two scenarios because we didn't have all these past observations of the shower we need to calibrate the simulations. So we made our best guesstimate and we waited to see what the observations said. And actually, so GMN and other networks like IPRMO or CAMS confirmed the enhanced activity of the Thor Hercules in 2022, and they allowed us to go even beyond that and realize that we first saw a first peak. We saw a first peak of activity that was caused by trails released from the comet before the breakup. But the data confirmed that the main peak of activity we saw in 2022 was due to meteorites ejected during the fragmentation in 1995. So that was pretty cool to see that we're able to model this very complex case of a fragmenting comet. We even done something a bit harder than that, which is predict the burst of a new meteor shower. A few years ago, Kwanzi Ye analyzed the outburst of Comet 15P Finley in 2014 and 2015 and suggested that the material released during the outburst could produce a new meteor shower on Earth in 2021, a shower we call the ARID. So we did the model similar in the same way that I exposed before. And we predicted the birth of a new meteor shower on October 7, 2021. But the shower was expected to be really hard to observe because the meteors had a very low geocentric velocity. So only the largest one would be easily detectable. And the super-radiant location was right in the middle of the Pacific. But somehow some video networks like CAMS in particular and some and the radars, even Seymour in Canada, were able to detect this shower and confirm the birth of the ARID meteor shower. So we decided to renew the challenge this last year, a few months ago, with Comet 46P Virtanen. Virtanen was the initial target of the Rosetta mission. And Jérémy Vaubaillon and other modelers found that material released by this comet could again give birth to a new meteor shower on December 12th, so past December. We did the model and the situation was very similar to the ARIDS, very slow geocentric velocity and a super-radiant located south of Australia, but luckily this time GMN was here and only a few minutes after the shower we received confirmation from Dennis that some cameras located in New Zealand and Australia successfully detected the shower. So that was really exciting. So in summary, because we're a bit ahead of time, yeah, we know that realistic models calibrated on long-term consistent meteor observations now allow constraining the ejection processes at the comet, sometimes for thousands of years. So when we do these stream models, we're actually reconstructing the unseen history of all these parent bodies. And the improvements we've made in meteor stream modeling also have significantly enhanced the accuracy of the forecasts we're producing for meteor showers, either in time or intensity. And this is important to help space agencies mitigate the threats that are posed by these objects. We're now able to handle some complicated stream scenario formation with some confidence. So complicated cases like fragmenting comets or never observed meteor showers. And developing these accurate models are necessary to protect the spacecraft because we know that the meteorites, the spacecraft are hit by the meteorites. The European Space Agency satellite Olympus 1 was lost in 1991 as a consequence of a Perseid impact. We also know that the James Webb Space Telescope gets hit by micrometeorites tiny ones several times per month. So we need to develop these accurate models to reliably predict where these dense streams are moving in the solar systems to protect the astronauts and increasing number of spacecraft we're sending up there. So that's why I'm really excited to see all the nice data that is gathered by GMM, because our ambition is to extend these models to all the comets and the whole inner solar system. And we really need the data you're gathering to have strong observational constraints for our models. So thank you. Keep up with the good work and keep observing.
Amazing talk, Orion. Thank you so much. I hope, we only have maybe a few years of data at this point, but maybe at some point we'll also have 35 years of data, but we'll see.
But I'm already using it everywhere, so.
That's awesome. Thank you so much, Orion. Are there any questions for Orion? We are now in the break, so I think we can directly ask questions now. There are also breakout rooms that are open for every single talk. So feel free to hang out there. The breakout rooms from the previous session are also open if there's something that you want to continue discussing. So I am opening the break officially, and then we will, let's reconvene in about 10 minutes. I'm gonna fix the time, and then after the break, we have one more talk, a last arrival. It's about the recovery of 2024 BX1. And then we're going to do a little group photo on Zoom. And after that, we're going to have the unstructured workshop, Q&A, et cetera, et cetera. So thank you, Oriane. If someone has any questions for Oriane, please go ahead. If not, let's take the break. Thank you. I think we're all good. There might be some in the chat, but thank you so much, Oriane. Get better soon.
Thanks.
He's got one more talk, and they're on break right now.
Yes, we are. I think you're good to go. So go ahead.
So, hi everyone, my name is Bence Gucik, and I would like to give you a very short briefing about how absurdly fortunate we have been with my friend Zoltán Balla to recover the second biggest piece from this meteorite fall. So just a quick note, this asteroid was discovered on the 20th of January by the professional astronomer Christian Czarnecki, just a few hours before impact. And the first stone, the first meteorite, was found by a professional Polish team on the 25th of January. And it was a very important information because at least we knew what to look for. So our reasoning was that the bottom side of the stream field is a very woody, foresty area, and there might be not much competition because the overwhelming majority of the searchers wanted to avoid the woods. And it was a majestic experience to actually find this rock. So the terrain is quite hard to navigate. It's systematic research. I mean, going back and forth in lines is almost impossible. But I think that the forest itself is a very well searchable because the ground itself is a very well searchable area for the several hundred grams stones. Sometimes it was very tough to navigate, but I would say it wasn't as bad as we expected it to be. So the stone was recovered less than 1 hour after we started searching, and we could not believe that we actually found it. You can see the disbelief on Zoltan's face. But slowly we realized that it was really the meteorite that we were searching for. It's not that big. The initial weight was around 114 grams, but it shrank a little bit because it is constantly losing moisture. This is the in situ image. So it doesn't make any craters or burn anything or sunk into the forest floor. It just simply sits on top of the leaves. And the material itself is extremely fragile. These tiny pieces you can see on the leaves are from the meteorite, very tiny sub-millimeter fragments, mainly from the fusion crust. So it's an extremely fragile material. Here you can see the stone itself. They are full of these B crystals. These are anstatite crystals, magnesium silicate crystals. And it has a very unusual glossy appearance. It's very shiny. It's because almost 100% of the stone is covered in a transparent fusion crust. A closer look, you can see the contraction cracks. And inside the fusion crust, you can see very tiny bubbles, just a few tens of micrometers in diameter. It is because it clearly shows that during the ablation phase, it doesn't just melt, but the very outside of the stone is literally boiling, and those tiny air bubbles are trapped inside the fusion crust. Also, the stone has very strong sulfuric smell. It's not just barely noticeable. It's very strong sulfuric smell. I assume it is because of spontaneous decomposition of sulfide minerals, but of course it's not confirmed. Our second finding was actually it wasn't our finding. I was in contact with Andreas Möller, who was also searching the field in a separate team, and we exchanged coordinates with each other. And at the end of our second day hunting, we decided to go out and search one of his coordinates because we knew that his stone there was broken, simply shattered into pieces. And miraculously, we found many tiny fragments. So one takeaway is to always carefully research that area. I have contacted Andreas about this finding, and he was kind enough to let us keep those tiny fragments. So it's not technically our findings, but right now we have several small fragments from this find. After this find, our friend Zsófia Bíró joined us. He flew out into Berlin after us, and we were searching on the fields. Now, these fields are extremely enormous. You can't really see that from the strewn field area. These are gigantic plains, and that's why, because it's very tough to search every square inch of these fields. It is still possible to find meteorites, even though after many dozens of people were wandering all around for basically weeks. There's still stuff out there. And it's a bit funny picture. I will title this picture "Searching Hard." We encountered the German volunteer team, and it looks funny, but seriously, this is the only way that you can do it. I mean, we are talking about stones with a diameter of a little bit over 1 centimeter. These are very tiny stones, so very difficult to spot them. Also, a huge takeaway from these experiences that direct sunlight is basically your biggest enemy, because it creates very strong shadows with strong contrast, and it further hardens the recovery efforts. And also, fields are very tricky because there are there are a lot of metal wrongs. This is my yeah, like zombies. This is my my favorite meteor wrong. I almost believe that it was a meteorite, but if you see carefully, there isn't a glossy fusion crust on that. But here is a real one. It was Zsófia's find on the last day. It's a beautiful roughly 5 gram piece. It also had a very strong sulfuric odor despite its small size. And you can see it's full of contraction cracks. It's very interesting because this is a very fragile and low density material. And usually contraction cracks are only formed inside or on the fusion crust of the meteorites. But this this material was so fragile that the contraction cracks simply cracked the whole interior of the meteorite itself. And since it was full of cracks, and at the time of the falling, the ground was probably frozen, many small stones simply shattered or exploded into tiny pieces. That's why we managed to recover many small fragments, basically meters from the original impact site, from the Andreas Müller finding. This is our little team. Zsófi in the middle with his beautiful stone. We also went back with my friend Gábor Kővágó a week later, but we didn't find anything, despite the fact that we know that we were on the right places. But it's all about basically just pure dumb luck. Another important takeaway for me was that it was extremely exhausting mentally. At least for me it was, because you need 100% concentration in every second, and full of metal wrongs, full of contrasty shadows. It was a challenging experience for me. That's basically it. Thank you very much for your attention.
Thank you for your talk. Yes, thank you for sending in the intention to give a talk a bit late. I think it's always a good thing. We would like to hear all sorts of perspectives, and you have your talk from an amateur perspective, which is an incredible story of finding this unique rock. And in the second section, we're going to have Dr. Peter Jensen tell us about the kind of professional side of things from his perspective. So right now, we are in a time where there is time. And before the group photo, are there any specific questions from Bence here before we move on? Feel free to raise your hand, unmute yourself, just go ahead. Okay, I'm gonna take that as no questions, and let us take a group photo now. So I'm going to switch to gallery view, and I kindly ask you to turn on your camera so we can see everyone, and I can take a little screenshot. Let me see, there are 2 pages here, so I'll have to do one and the other. So we're gonna start in about 10 seconds. So I'm gonna do a little countdown, wait for everyone to turn on their cameras, configure all cameras, everything you have to do, and I'm gonna take a screenshot, okay? I'm gonna do 10, 9, 8, 7, 5, 4, 3, 2, 1. Okay, so, let me do it again. Okay, so this here is the first page, and I don't know if you're on the first page or the second page, so please bear with me. I'm going to do it again. I'm going to switch to the second page, and I'm going to do it again now. Okay, and then save, and we're good. Okay, thank you so much. So now's the part where we have our unstructured workshop. This can be where we, ask whatever you want, bring up any issues. This might be a bit of a boring part for some or an interesting part for some. But we do have a couple of action items that people have sent in advance to discuss. And there are a couple of questions. Maybe we should start with Luke, are you here still? There's so many people I can't.
I'm here.
Oh, okay, great. So there was one item that, something that you recently discovered, and that's something that you led the charge to develop a new graph that is now automatically generated for every station, and that is timing, right? So you really looked into how accurate timing of RMS cameras is, and you actually develop a capability to radically increase the timing accuracy to an order of just a few milliseconds of these IP cameras. So is that something you would like to say more about? Maybe show a couple of graphs, or just kind of take it easy. And if anyone has any questions, just kind of chime in. And so we're just kind of generally talking about timing of these cameras, just for general context.
Right.
We know that our timing is not good. It can vary by orders of like 100 or even more milliseconds. It can also be a bit late. And IP cameras don't have good timing at all. And that's something we take into account when we do our trajectory computations. But look, you were able to find a way to make that much better. So take it away.
So yes, first of all, the way I realized there was an issue was with the aircraft position overlay. I realized that occasionally the aircraft position overlay would not be exactly on top of the light from the aircraft on the pictures. That the predicted position would be ahead of the image, meaning the image is late. And when I digged into it, I realized that if for some reason the system cannot keep up with the camera frame rate, the frame would start to accumulate in a buffer, and the code would timestamp the image when it's retrieved from the buffer, and that image may have been an old frame, so it would timestamp an old frame as a new frame. And that would happen on slower machine that may be slow because usually because of the SD card or the USB drive is getting slower. As the machine are getting older, those SD cards, those flash drive type memory gets slower over time. And so Dennis and I developed a method to find out if that's happening on your machine. So if you now look inside your archived file folder for the night run, you should see a file called, help me out here.
FF timings. Do you have an
FF
example you can show?
intervals. Yes. So it would be your station name with a timestamp and then FF intervals. And let's see if I can share one. Bear with me 1 second. I wasn't fully ready for this, sorry.
Yeah, no worries.
So up here, back up.
Maybe I can pull up some from GitHub that we have over there.
Yeah, so here's one. Okay, let me share that. Share screen. Okay. So that's what the graph look like. So it's showing the interval between every FF file that the RMS software is timestamping. So ideally,
and for context, right? So at 25 frames per second, a block of 256 frames should be exactly 10.24 seconds, right?
Right. And so, so in this case, it's showing that the variation is, let's see, 24.99 frames per second with a variation of 15 frames per second. So this machine was having a lot of trouble keeping up with the frame rate of the video and was timestamping old frame as new. And so this graph that should show up in everybody's archive file from now on will tag bad FF file as red, and I will tell you that there might be an issue with your machine. So a normal file should not have any red in it. It should be nice and regular. So moving forward, we're working on avoiding this problem by timestamping a frame when it arrives in the buffer, not when it leaves the buffer, and that should in the future alleviate that issue. So my approach is to use GStream instead of OpenCV as a media backend, and that seems to work. Let me see if I can find an example. I'll go on my Pi to see last night's run. I'll try to share that.
So just for context, he developed a special modified version of RMS that we're planning to deploy everywhere. However, he does have a special installation of GStreamer that has an extra ability to adjust certain capture parameters and also timestamp the frame exactly when it arrives and not when it's read. So there's still a bit of a network latency inbuilt there, but that is pretty stable. And the scatter, when I think when he's able to find a graph, is going to be only on the order of 2 milliseconds. So when that difference is compensated for, and that's something that could be directly measured, we can have something that's extremely stable and very high accuracy timing on these ridiculously cheap IP cameras.
So that's the last night's run for me. So that's showing pretty much no variation. So I'm like sub-millisecond accuracy here.
Wow.
Compared to a regular run of the mill. So and I'm using a clock, a millisecond precision clock. I don't know if you guys can see this. To validate the data, I should turn my background off. You guys are gonna see the mess in the background.
For sure, it's fine.
So all right, so I've got a timer here that updates every millisecond, so I can double check the accuracy of the GStream approach. And it's pretty much within a millisecond now. So,
yes. So Murray asked if the intervals graph is going to be displayed on the web page. Yes, that's a plan to modify the weblog code for this to show up there. And for kind of normal cameras that do not have this extra GStreamer option plugin, the scatter is going to be a bit bigger, but it's not going to be as bad as that first graph that was shown. Everything should be well within one video frame, and there shouldn't be any issues. If your SD card is working well and if your Pi is not having any issues, but that is a really good diagnostic plot that shows, yeah, there we go, there's one. And here you can even see the kind of the reason why it's all in these lines is simply because that is the millisecond precision that is stated in the name of the FF file. So this is all well within, how much is there? Isn't it's even a few milliseconds, yeah. And that sorry, is that with the with the GStreamer too, right?
that I do not remember.
It probably is because it's so tight.
Yeah, that probably
is.
That probably is raw GStreamer, so that you can
Yeah.
adjust the pipeline a million different ways. So it's probably a GStreamer approach, but I don't remember exactly which pipeline this was in.
Yeah. Let me just I think Dave did send a few of these, but I can't see them now. So generally, everyone should go and look at these plots and see if there's a lot of red. Your SD card is probably on the way out, and that's something that you should definitely address.
Right, I should maybe show exactly where it's located.
Absolutely, yes.
So if you guys go to you guys see this?
Yep.
So okay, so if you go to home directory and then Pi RMS, so it's in your RMS folder, archive files, and then in your the night run, it should be somewhere in there. Interval.
I also found a couple of plots here that I can. It's from GitHub that I can show.
No, that's all.
Yep. If you don't mind, I can show it here. So if everything is fine on your normal setup, this is how the plot should look like. Everything should be well within 1 FPS. You can even see there's a these limits here show show the limits of I think plus or minus one FPS, which is 30. Is it less? About 30 40 milliseconds, and that is what we can expect. And if something is wrong, you're going to see these red marked dots. And there's, in particular, we found that some cameras have been configured to reboot during capture. And then what happens is that the camera is not available for a while, and that causes this big jump in time. And what you should do is you should reprogram the camera so it doesn't reboot during the night, but it reboots during the day when it's not capturing. It's worth saying that the reason why we're trying to push this increase timing accuracy is because we want to try to do other things with these cameras. It's important for meteors as well, but for example, imagine if we could do, let's say, asteroid occultations with these cameras and that software. I think that would be really exciting because asteroid occultations are kind of hard to do and also rely on telescopes. But imagine if we could stick kind of a longer lens on these inexpensive cameras and then distribute them along the occultation path and then have incredible accuracy of timing, and we could possibly get everything down to with what Mike has shown with these cameras, probably with the right combination of lenses, maybe even down to, let's say, magnitude 13 if we take like a narrower lens, which would be absolutely amazing and useful, and especially, as he says, for aircraft as well. Does anyone else want to add anything about timing or anything related to that? Okay, so did I miss some discussion here? Jesse, you say you checked and you have some red ones. Does that timestamping them on the way into the buffer and ensure that they are the right frame for unprocessing later? Does match the number of frames? Yeah, so I don't think that anything in the buffer is really lost and everything is in the right order. It's just the timing we didn't have a way of stamping them before they arrived in the software. But with his modification, they get stamped immediately when they arrive in the buffer. So even if there's some sort of processing latency or whatever's going on, they're gonna have the right time, and that's called presentation timestamp. That's something that he found in GStreamer. Apparently, it's also maybe an option in FFmpeg, but we still haven't found a proper way of using it. So Pete Ashman has a question.
Yeah, my question is, does this result in any actual data loss, any missing recording? I mean, obviously the camera reboots, that's missing data recording, but these timing errors, do they correlate with skipped frames and things of that nature?
I mean, it depends what the amount, what the actual length of the break is. If the break is longer than I would say a couple of seconds, I think things are going to start dropped off out of the buffer, definitely, before things get recaptured. But if it's shorter than that, it just means that the timing on the short time scale is not going to be as accurate as we want it to be. Now, in a sense, that as long as it's not longer than, let's say, a second or so, it wouldn't have any influence on too much on the meteor orbit radiant, because just the astrometric accuracy, it's not that accurate to so for us to notice these differences, and the solver is going to compensate for the differences in timing between cameras anyway. But that is definitely something that we want to avoid, right? And one thing that also we want to discuss is that going forward, we can't really ship this fix to have this super accurate timing to all cameras because GStreamer has to be compiled from scratch as far as I understand and installed properly, and that can be a bit tricky. So what we'll have to do is we'll have to prepare an SD card image with this installed, and then once RMS recognizes that it's installed, and then it's going to try run the camera with that, only then it can be used. So all the stations that are running currently, they're going to have this timing that it's pretty good, but it's not millisecond precision. But after this is addressed, we can achieve millisecond precision, which is crazy. So one thing, Luke, I think you just started telling us about that, is that you actually ran experiments where you had like a timing device, so you can actually see the difference and time consistency of individual frames. And that's something that Mike Mazer has also done, but I don't know if he wants to talk about it, where the goal is to achieve millisecond precision. Luke, can you say more about that?
Yeah, so this clock shows the time to the millisecond and it has a refresh rate of less than a millisecond. It's driven by the pi itself, so every top of the minute it resets the clock. So it's perfectly in sync with the Raspberry Pi that the camera is connected to. So even if the Raspberry Pi system time is a little off, that shouldn't matter for that experiment. And it's showing pretty good millisecond accuracy. Better than that, I can't measure, so I would have to build.
There's actually, you do find a constant offset. There's a constant offset, but the jitter is tight.
Right, the jitter is tight. There's a constant offset. That's a bit of a challenge because each time I restart the experiment, the offset is a little different. So it's precise around a millisecond. I'm not quite sure if it's accurate to. It's more probably accurate to 5 milliseconds.
5 milliseconds. Okay, pretty good. So Mike has his hand up. Mike, go ahead.
Yeah, sure. I'm just going to share an image from my screen here. Just one second.
Do it, yeah.
So yeah, the work that we've been doing, we're trying to get the timing as accurately as we possibly can for the SSA work. So what I've done is I've built essentially a time stamping device. It flashes an LED for a microsecond, then waits 9.999 milliseconds, and then flashes for another microsecond. I get a series of images. These are 250 frame stacks. These are the max pixel value. I can interpret a sequence of frames to get the frame start time. It's GPS synchronized, so it's good to within a few tens of nanoseconds. And I can then look at the timing error. Right now, I know there's still a few issues with the code, but right now you can see that this is 20 milliseconds here. And with the time stamping and conditioning that I'm doing, we're probably on the order of jitter that's less than a millisecond, but there are these little jumps occasionally that I'm not, haven't been able to explain yet. So this is something that is going on right now, work that we're doing to try to nail this down. And we've only looked at it for one camera type. We haven't looked at multiple cameras. And I'm not quite sure, how this ties back into the GStreamer. So I've done comparisons with presentation timestamping on, with it off, with the old way. With this way, I see a stable baseline and these occasional jumps. With the old way of doing it without the GStreamer presentation timestamping, I see a larger offset that changes when I restart the camera or start a new session, for example. I see periodic behavior in some of the instances, but things are much, much better with this presentation timestamping. So that's and I concur with what you're seeing. I was seeing originally RMS of about, I think, plus or minus 8 to 10 milliseconds roughly, with the either 347s or 385, if you get which cameras I was using. But that seems to be fairly consistent with what you're showing here.
Right. And another thing we found is that it's very important that the camera is set to PAL and not NTSC. in NTSC, it's at least the IMX221 on some chipset is acting very strange by achieving the frame rate by not showing one frame. So it's actually showing 30 frames per second, except it's not showing one out of 5 frames is being dropped. So it's very irregular. So super important that the camera is set to POW.
Yeah, well, that's something that we noticed also initially, that some, at least cameras at the beginning, if you set them to full HD, then you would start seeing weird things. At 720p, they were fine. And also, when you say that maybe it drops a frame, we also notice that sometimes it duplicates a frame. Instead of actually dropping it, they just say 5 out of 6, and then the last one would just be a repeated frame. And a person who's watching this on a screen in real time in usual IP camera applications, that doesn't matter. No one's going to notice, but for us, it makes a big difference. So that's a great finding. Is there anything more that someone would like to say about timing? I see that Mark shared a plot, so I guess Mark, that's yeah. So Murray also says the most common system by occultation people is an analog camera whose video stream goes through a GPS timing module, and then it's time step each video frame. That's something that we also discussed, and the way we do it in the professional world is that we have industrial camera with the GPS module, and then timestamps each frame directly in its metadata, and you can tell which. But I mean, we are not spending thousands of dollars per camera for our amateur applications, so we have to find a way to do it on the cheap. And ideally, we would have some sort of a CCTV IP camera expert who actually knows what they're doing but here we're maybe a bit just kind of trying to figure out what's going on around. So Michael O'Connell, you said that there's a QHY174 GPS is gradually getting more popular. Is that a particular camera model, or you can feel free to unmute yourself and just.
Yeah, it's a camera model we use for occultation work. It's a CCD or CBOS unit, but like you said, with the built-in GPS.
GPS, yeah. It would be good if we could, yeah, so that's probably the IMX 174 inside of it. That's something that it's been out for a while, and unfortunately it's not nearly as sensitive as some of the newer IMX models, but hopefully maybe in a few years these things are going to become more available.
But if we could get a lower cost unit that we could reliably attach GPS and timing info to, that'd be fantastic.
Yeah. It's that, or run tests and then see what the latency is. So because with the G-Streaming module, and as Pete Ashman says, it should be in the new bookworm image, and I absolutely agree. We just need to do a little bit more testing, but then install it and deploy it. And when we roll it out, everyone has access to this new option. The only thing is there still needs to be an absolute timing offset applied to the video, because you're looking at here on these graphs are just relative timing offsets, but there's also an absolute time that passes when the frame is converted on the camera, travels through the network, and then is received in the buffer. But that's usually on the order of maybe tens of milliseconds, and that's something that we still have to figure out if that's something that changes over time. Is it stable between systems, stable between camera models, stable between network configurations? If it's not, then maybe we have to find a way to calibrate it. And one way to calibrate it would be on an object of, where we know exactly where it's supposed to be at what time. And there are, for example, calibration satellites. We know exactly they're there at this time, and then we can look at the difference of position and determine the timing that way. So Damir has a question. Damir, go ahead.
Not question, just statement that I tested those fixed offsets delays between real time and what we actually see as time when we are observing things. So it depends strongly on the camera mode. I checked that out on lightning measurements or by looking at light curves, and you can see that for all the types of cameras, I think we still have some 290 ones from the beginning, but the difference between 291 and 307 is a significant one. So it depends on camera, and I think even on is it running on Pi 3 or 4. So basically, all the models have some delay of about 2.2 seconds, while newer ones are around 1 second. 307 on Raspberry Pi 4 has typical fixed delay of 1 second, and it's pretty much stable. It's not varying too much. If somebody would like to check it in a more consistent way, I suggest to check out when you have thunderstorms and look after light curves in case you have some data coming in from guys observing lightning during thunderstorms. So you may possibly find exact timings down to a millisecond. I know Blitzorton provides data, but they actually detect only about 10 to 15% of lightnings. So but that would be the way you will find common events, and then you can check out for exact fixed offset.
Yeah, that's an excellent idea of the way of synchronizing the timing on a kind of a wider scale across all cameras. That's great. So a couple of other things that are in the chat I see is that Roel said that, you know, if he can package it, everyone can install it without rebuilding the system. So Luke, maybe you can give a little comment on, you know, what did you have to do to install it? I know that, you know, a couple of people had issues with actually getting it to set up. So
I had to build an open CV package with GStream in it.
Okay. So we do have a script already in RMS that builds OpenCV with FFmpeg. And I wonder if that can be modified.
Yeah.
So it includes GStream, right? Did you use that one, or you
I
used something
updated
else?
that. I modified that one. Yeah.
You modified that one. Okay. And was it modification was substantial or?
No, it was.
Okay.
I would have to read my notes. I don't want to say anything that I'm not 100% sure. Yeah, I modified it slightly, and no, I don't want to. I'm not sure 100% right now, so I don't want to say that.
Okay.
But it was not a big deal. I didn't have to spend 2 hours building something from scratch. No.
Yeah, that's definitely something we can discuss, and at least if we're not gonna deploy it automatically, which I'm very much against, at least we can update the version that is in RMS repository and then tell people this is how you can do it, run it, and that should be it. Murray, you have a question? Go ahead.
Not so much a question, just a comment. Going back to the idea of observing occultations, which, if you saw my earlier comment, is my other big hobby. Occultations involving bright stars, like we see at the gym in cameras, which is down to say about 6 magnitude. In any one location, you might see 1 or 2 a year. That's about the frequency. But if you can get to the cameras that were mentioned in the previous talk, which you're getting down to 10th and 11th magnitude, then you're talking about 1 or 2 every couple of weeks. So it starts to be getting worthwhile doing that science.
one thing that I had in mind is even having, let's say, if we can push it down to, let's say, magnitude 13, and that really opens up the number of occultations. It could also be done in such a way where these cameras don't have to be permanently mounted. We could, or someone or some organization could literally have 20, 50, and then when we know an important occultation is happening, they literally ship it to amateurs in the area. They go set them up and then do the observation and then ship them back. Does that sound reasonable, or is it just a crazy idea?
No, something not similar to that has already been done in the occultation
Okay.
community, but these camera setups look like they're a lot more complete and foolproof compared to what had been done before. And there are some people who own 5 or 6 cameras, and they do exactly that. There's a lot of traveling in one night.
Yeah.
But with the fact that we've got such a wide field of view of these cameras, it makes the setup very easy. You don't have to worry about pointing at the star exactly. You just point it roughly in the right part of the sky and then go on and set up the next camera.
Yep. Yeah, that's definitely what could be done, and probably some sort of an extension at some point in the future. Okay, we do have a few other things to discuss. Does anyone else have any other questions or comments about timing that they want to pitch in? New ideas or? Okay, I'm closing this topic then. We can always return. And also there's another thing that Luke found, and that has to do with our astrometry calibration, which I found really, really interesting and compelling. And that is that it appears that that drift that you've been seeing on those plots every day, that is an artifact. It's an artifact of something that we do not think to take into account, or I guess of a way how we set the reference point. And if we were to fix this, which we will, the drift is going to be much lower on the order of, let's say, arc minute instead of 10 arc minutes. And it would open up many more possibilities. And that possibility is observing fireballs during the day and having good calibration for them instead of having something that could be off by a lot. So Luke, would you like to summarize whatever you found, what you found, and what should be done? Yeah, go ahead.
So see if I can share a screen. If you look at the calibration variation graph on the let me pull one up. Go back to my amazing presentation. There we go. So you guys see this? So this is the typical calibration variation that I guess everybody sees. That's the experience everybody's having? I was curious by the shape of it and how repeatable. Why is it the same for everyone? That if it's an issue with thermal expansion of the camera bracket or something like that, it didn't quite make sense to me. And also it was very faint, but I noticed that I had a little bit more drift during the day than during the night. During the night, the camera, the pointing is constantly updated with new when it matched new stars, so it's not a problem. But during the day, it drifted a little bit, and I was wondering why. What I think is happening is that we are calibrating against a catalog of star in J2000 in the J2000 epoch instead of the current epoch, and so the pointing has drifted since January 1st, 2000. Is that what it is? So by about something like 19 arc minute. And so I think what's happening is that we're chasing this error since J2000. And so when I convert the catalog to current epoch, so that know that the array deck for each star is in current epoch, I get this instead. So if you compare the scale, so this was 12 arc minute of variation about, and this is what I get with the precession equation that's in the code, which doesn't include mutation or anything like that. No, it's ideally we would be using our AstroPy to get a perfect precession correction. But so it's much closer. So during the day, I'm expecting that it's only drifting by this much now.
So I believe the implementation that we have in there, I implemented from the Meiosis book, but it should be good to within maybe a few arc seconds.
Okay.
And in WMPL, there is an implementation that uses all the full notation and everything, and it should be good within a fraction of an arc second.
That's plenty good enough.
Yeah, for our accuracy here.
And then there's refraction, so we can.
Yeah. One thing that we could, I thought about how to apply this change, and things are much trickier because initially we've chosen this way because the way we're doing not just this astrometric calibration, but also work that we've done for dash cams. And there we have to calibrate things on points on the ground. Then when we convert geographic coordinates to ECI coordinates, and they have it's the same coordinate system as like right ascension declination at J2000, then it becomes much more complicated. But we could, when we make this change in the code, we would have to also make sure not to break the dashcam code in a way, and not to break any of the currently existing plates. And ideally, we would still have, I guess, the reference pointing in right ascension declination at J2000, but then just correct it for whenever it needs to be done. Because let's say, I make the plate now with the current epoch, right? At the current pointing, but then this plate becomes 5 years old, and then we again have a pointing issue, right? So I think we should keep some reference, but not kind of correct it forward in some ways as we can. And that's if we can keep the pointing from not drifting artificially, which is an amazing find. And I'm kind of happy that you were able to dig through the code, understand what's going on, and find where the issue is. We can then there's been some discussion, and I want this to be a segue for example, observing during the day. And I know there are some people who are already switching their cameras to their day mode, and they're recording the video. Of course, there's no automated procedures of any kind, but if there is a huge fireball that's observed during the day, the data is going to be there. And then we can apply a little of the same plate without almost any corrections and calibrations and any drift that could be used. Of course, these fireballs are exceedingly rare, and the limit that we found from doing some daylight dashing calibrations is that the fireball would have to be brighter. Damir, what was the Nova Mesto? I think at least minus 14 or brighter. It would have to be literally a meter-sized object, which.
Oh, Nova Mesto was far brighter, but I think we
because of that peak, though. Because of that.
No peak. No. I think we have it at somewhere at minus 11. Let me check. I will be back.
Yeah. Check it quickly. It's a nice option to have, but I feel one is not going to see a lot of daytime fireballs because there's just the limit of the background. The background is limiting your sensitivity. Pete Ashman, go ahead.
Just want to bring something up, make sure I understand correctly.
For sure.
A lot of the camera motion we see in that one plot over the course of the night isn't simply the motion of the camera itself, it's the motion of the whole structure it's attached to. expanding and contracting thermally.
Yes, so
That's
the
my
motion,
understanding.
yes, so that's true, but the magnitude of that motion is not 10 arc minutes, it's about 1 arc minute. So what we've been claiming to see for years, that thermal expansion, it's still there, but the magnitude of it is much, much smaller. In fact, most of the motion that we see is because of an effect that we haven't taken into account properly. And that's going to be fixed, and then it's going to be as best as it can be. Murray, you have your hand up. Go ahead.
Yeah, I've got to admit I'm a bit confused or surprised when you talked about it being precession or mutation, because that shifts the origin of the reference system being used. So it affects all stars equally. So I don't know why we would be seeing a drift overnight, especially when precession takes order of 10,000 years to complete a cycle.
It is first, when Luke was sending me emails and telling me that he found this, I did not believe him. I was like, no, precession is like, right? Like, it takes decades to see this. The effect is how can I describe it? The issue is that the way we define the center of the field of view is we say we make the calibration, and then we define the origin of the coordinate system as right ascension and declination at J2000 in the middle of the image. But the issue is that, this is where this right ascension declination was at J2000, and then the motion of this, you can imagine there was there's some sort of like a great circle across the sky through which, the declination is going to stay the same, but the right ascensions are just going to shift throughout the night just because of the sky motion. But the issue is that the origin, the position of this axis around which the sky rotates has changed. So over the course of the night, what happens is that, the reference field of view, the right ascensions don't go this way, but they go slightly this way. And that's why you kind of see this offset. It's kind of wobbling and not going straight in a sense. It took us a while to understand what's actually going on. And what we would like to do is just kind of still keep the right ascensions and declination reference in the middle in J2000 as kind of a hard point to hold, but just correct it for whatever the rotational axis is, instead of just kind of keeping it straight. So just to kind of the reason why that was chosen is because it's really easy right now to compute the right ascension in the middle of the field of view over any difference in time, and that is you just kind of add the hour angle, just kind of the difference in hours between the reference point and whenever you're trying to compute the astrometry, and then you just kind of add it to right ascension. But the problem is it's not that simple. In fact, there's this other effect that you have to take into account. Now, there's a way to make this all go away and just take everything reference in azimuth and altitude, apparent azimuth and altitude, but then you can start looking at things from a different perspective and say, well, yes, but those apparent coordinates have to take refraction into account, and then there are issues when your camera is pointing really low, especially if you're trying to do some dash cam calibrations, et cetera, et cetera. So that's why we're kind of holding J2000. So Murray, go ahead.
Yes, yeah, I suddenly realized why it was happening. I'm used to dealing with tracking cameras in my hobby in astronomy, where this effect doesn't take place. But if you have a camera which is not mounted on an equatorial mount, like an alt azimuth one, in other words, it uses a horizon as its reference, then the field of view appears to rotate around the center of your camera as the night goes on.
Yep.
So I suspect that's exactly what we're seeing here.
Yep. That's what it is. Yeah. So just for context, this method of astrometric calibration that we're using was actually Damer can speak to it. I don't know if Damer, did you invent it? Where did you even find it? I don't think we can even find a source of where that came from. And we just kind of implemented it into GMN, made a couple of additions and fixes, and that's what we use now. But I don't think anyone ever kind of questioned what's going on here and even saw this effect coming. I don't know if Damer is here. I don't. Yeah, he's here, but probably maybe. Damer, are you there?
Yeah, I'm here.
Yeah.
But I don't understand exact question. What is the question?
Oh, can you just tell us shortly about the origin of the astrometric method that we were using? So you came up with it. You gave me the source code of some original thing.
That one.
And can you just tell us how that came to be?
Oh, well, long story. Basically, when I started, I used code which Seiichi Yoshida was used for his, I think it's Pixie project. It's some Java script or something like that. Actually comes with the source code available. So I'm not a Java programmer, but I somehow know how to read this stuff and actually found out how he was doing it for his I think it's asteroid observations. And then it basically goes, you pick do the astrometry on the star field, fix the center of the image, and correct it for basically for time passed from reference image. Now it is important, however, to look after in which coordinate system you are working. Which for pointing, are you using as a reference point azimuth and so horizontal system, or you are using rectascension declination? I think back in CMN we used rectascension and declination, not azimuth and altitude. But somehow I think we are referring to azimuth and altitude in GMN.
No, we're not. It's all rectascension declination. That's where the problem comes from, actually. We could actually make a proper correction looking at the altitude and azimuth and match it between different times of consideration, and that would definitely fix the issue. The issue is that is computationally intensive. I would rather have a elegant solution mathematically than kind of brute forcing it to snap to where it's supposed to be. We can fix it today. It's just it would be kind of nice to fix it long
But
term.
it would be nice to have a deep understanding why is this happening, because I don't understand. We spoke about it, and I really don't understand where the issue is there.
Okay.
So what is important at the moment to see for everybody to know. So each of our FF files is being processed correctly. So stars match, even meteors are being reduced incorrectly. It is that somehow pointing gets affected by this perception. I don't understand where it is. I should go dig deeper in our current code to see why is that.
Yeah, we can probably chat outside of this meeting to properly explain what's going on. The effect is quite bit difficult to understand, but it's there. Okay, maybe we can switch the conversation to daytime observations. So Damer just sent me. Sorry,
yeah.
Damer.
Yeah, go on. Okay.
So you just sent me a light curve that we derived from Nova Mesto. So would you mind showing that on sharing your screen and just quickly showing that? I can do it too, but. Okay, well, I guess I'm doing it. Let me just quickly. Oh, there it is. Perfect. So, when I said that during daytime, the fireball has to be really bright to be observed, the reason is not because the camera is not properly configured. It can be configured to record during daytime. The issue is simply that the daylight sky drowns out objects that are fainter than these extreme bright magnitudes. So to observe a fireball during the day, it needs to be -12 here, and that was derived on dash cam camera where the background daylight sky was not that bright. And you would at least have to have, let's say, a magnitude 14 or magnitude 16 fireball to get any useful points along the fireball's track, because -12 is just kind of the bottom limit. If the fireball was -12, -13, you would have a point or two, and you wouldn't be able to reconstruct the trajectory quite well. So that's the point that I'm trying to get across, is that the fireball has to be extremely large, extremely bright. There's a way of getting around this, and that is to have a special filter to get rid of the atmospheric lines and just to focus on the lines that the fireball is in. Murray, you have a suggestion? Go ahead.
Oh yes, it was almost anticipating what you're going to say, but a bit cruder and cheaper is have a broadband filter to filter out the blue light, because that's the brightest component of the light in daytime sky. So you're just looking at the red, and that might improve your signal to noise.
Yeah, that's actually a pretty good suggestion.
And it's cheaper than trying to get an interference filter.
Yeah, absolutely. So one thing it could be done, but then I guess the IR filters that come with the cameras would have to be taken out, and a little bit of the red filter could be put in. Bill Cook has a question/suggestion. Bill, go ahead.
Just a comment. We tried developing daylight meteor cameras on a lark using a narrowband oxygen filter, and that puppy didn't see anything. The narrowband filter just cut out too much light. But so our efforts in daylight observations failed, but we were not trying to see, we were trying to adjust the background, right? But the other comment I want to make is something the good Dr. Brown reminds me of on occasion. When LSST comes online, right now we're detecting 1 meter object per year, roughly, extra atmospherically. But when LSST comes online, that's going to extend our reach by 3 magnitudes, which means we're going to have 10 or more of these events per year. And I think the development of a daylight camera with the notion that, hey, we will be prepared if we receive like 3 or 4 hours warning of an impactor coming in to adjust camera pointing or something would be extremely worthwhile if it comes in during the daytime. So just a point.
Absolutely, yes, thank you. That's great. One thing that we would have to do is, and that again would have to be on the SD card images going forward, is I think we would have to configure a RAM disk where videos would be streamed, because as far as I understand, SD cards don't like continuous writes. And then once we have the RAM disk, there would have to be a script taking it, putting it on the SD card. Now, one thing that I would love to hear is that people who are already running it in this mode, and I think Dave Rowlandson is here. What is the data size? So, what kind of impact does this have on storage? And would it be viable to keep a day or two of video recordings from daytime on the Pi, or is that comparable to nighttime FFs, or is it much less, much more? Dave is here, or anyone who wants to speak about that?
Yeah, I just run the exact same algorithm during the day, so it's the exact same footprint personally. So it creates FF file. I'm hoping to catch one. So I watched the time lapse from the FF file to catch one. Like I've seen a few throughout my lifetime during the day, so I'm hoping like, to catch one on the camera.
Oh, nice.
Especially while flying.
Yeah, so it would be interesting to try to. So the reason why I don't think that FF files are ideal for daytime is because you try and capture fireballs, and FF files are terrible for fireballs. And because the daytime sky doesn't have a lot of things going on, it's usually mostly just uniform. Um, Probably the video size that the H.264 compression is going to work really well. There's very little noise, there's very little things going on. I probably think the video size would be tiny compared to nighttime video, which we tried recording, and we still have it somewhere, which can be quite big because there's a lot of stars and a lot of like bugs that you can see during the night, and simply noise that doesn't lend itself well to any sort of compression. Tends to pump up the file size. That's something that we can definitely try and test.
Yeah, I just checked. I've got like 10 megabytes for day and 12 megabyte for night. For a time lapse.
Oh, for time lapse, I was actually thinking about actual full 25 FPS video that could be streamed and saved to disk. We do have a couple of scripts where you can go and capture video, and it's saved in, I think, 1 minute blocks. And then I think it's kept for 7 days or something like that. Damir, go ahead.
In case we would be going towards daytime observations, I would strongly suggest we just capture videos because we can easily reconstruct an FF file from MP4 video. The other way doesn't go. So in case we would like to have some observations we may use and have decent quality data, then we should go with complete video. And as Dennis said, I don't think those files would be bigger than FF files. On contrary, they should be significantly smaller.
Yeah, I think that, for example, during a cloudy night, when there wasn't much going on in the sky, the MP4s for 1 minute were like like 100, 200 kilobytes for a whole minute of data, because there's just nothing's going on, and they compress it quite well. So that's definitely something we can look into. And again, we can keep it still running in black and white mode. I know people like color, but doesn't help in any way, and it would just pump up the video size, if that would help to reduce the video size, which I think it probably would, because then the Luma channel would contain all information, and everything else would just could be compressed down to 0. Okay, so I think we are probably drawing to a close here for the first workshop / Q&A, and I would definitely like to open it up for any other questions or points of discussion. It can also be like Festivus. It could be like airing of grievances. This is the exact time to do it, or some new crazy ideas that you're looking for someone to do and help you out. For example, I know that Damir in particular, he's crazy about meteor showers, and he's thinking about maybe creating a little meteor shower work group. So Damir, is that something you want to talk about now?
I'm not crazy, literally, but yes, interested in meteor showers for sure. And the idea was to have a group of people devoting to not search for new ones, because that will happen once new ones occur, but to go from day to day and check out for all those small bulbs we see on our daily plots or monthly plots. Let me share it for a moment. So this one.
Yeah, go ahead.
Yeah. So okay, this one we don't need. So we have things like this. It doesn't like zoom. It goes a bit slow. So we have some concentration of radiance around some point, and okay, we know this is a meteor shower, and it is DNO. Here is our search tool. We open the search tool. We can easily sort it out from coordinates we have here. Now, there's lots of situations where we have such concentration of radiance, and it is most probably some meteor shower. Is it a new one or old one or known one? We don't know because in not all situations such groups of meteors are being circled and have its name or abbreviation besides it. In case like this one, so this is a known meteor shower. This is also a known meteor shower, but we simply don't have them in our meteor shower database we use for shower association. Now, I would like to find a group of people which would daily check out for daily plots, see if we have a meteor shower known at this position, and simply say, we see this meteor shower from today and up to, let's say, 8th of March. And to have a Google Sheet where we will add those known meteor showers to our database. So when it happens, not for us to check is this new one or what is going on. This should be very helpful in sense of not only us having this database, but it will be very helpful in order to clear out the meteor database. MDC database, which is full of I won't be
So
rude,
just for context, if just for everyone, if you're not if you don't know about much about meteor shower work, but the International Astronomical Union has a table of meteor showers, and that table is quite messy, and a lot of people are trying to clean it up, make sure that the showers that do not exist are removed from the table, and showers that actually exist are well documented, that the radiant locations, that the activity period is well defined. And that's something that I think several groups are trying to do in separate efforts. But I think we are currently at the state where our data volume is such that we see meteor showers that no one else saw before, or at least not in these large numbers. So it is hard work, but it's literally just quantifying, saying this shower was active at this time, these were the radiant locations, this was the activity period, and that's something that could be published and the International Astronomical Union can be informed. So when people like, for example, Oriane, go back and look through historical records, or whoever's going to be looking at GMN data in 10, 20, 50, 100 years, can say, yes, this is what was observed. Maybe the original plots are not available anymore, but at least someone measured it and this metadata is still there, and yes, the activity occurred, the activity existed. And it is just for us to know when we see the plot that the software automatically identifies known showers, and of course all the unknown stuff pops out, so the community knows that something new is going on. And right now the table that is running, so there's a table that's used to mark all the meteor showers that you see there. It's something that we've done manually as best as we could. And we kind of want to go back through a couple of years and do this work of manually identifying showers, update this table and say, this is the ultimate table for that was done in 2024. These were all showers that were measured between these and these years, and these are their very accurate parameters. And that's the whole point of it. I think that's
Yeah, it's not a job that will be done in a week or two, but it's a job that we can do easily all year long, as we are supplied with new daily plots just to recheck it. Okay, currently we have active 10 showers, and just to follow them through the activity. Spring is good to start with because there are small number of them, but may become tricky during winter, autumn. Winter could be tricky. But in this way, we will actually filter out the complete Meteor Center database, so we could say, okay, GMN with its more than 1 million orbits says that in its database, from its database, we can see these 500 or 600 of meteor showers as existing ones.
Yeah, that's if someone is interested in meteor showers and wants to do some work, I think they should get in touch with Dame. Okay, great. And I see another item here, and people are asking about data access. You know, what about all the data that got uploaded to the server? Can we download that? So yes, your camera has access to the user directory on the server. And currently, it's all done through SFTP commands. If you write SFTP camera code at gmn.uw.ca, you can go in and there's a folder that says processed. And in there, you can find all data that has previously been uploaded to the server. You can just download all of that, just the archives though, but they contain everything of any importance anyway. We do have plans to start moving this data because the data volume is becoming ridiculous. Right now, I think it's over 60 terabytes. And as you might imagine, that is becoming hard to manage and make it immediately available to everyone. So we are thinking about moving this data to long-term storage, basically tapes. When one cartridge can hold maybe around 18, 19 terabytes at this point. And we're planning to dump all data there from it's older than maybe 1 year. And then we would have several backups of this data, and it would be kept in good conditions in perpetuity to make sure this data survives long term, just because there's so much of it. And with the number of cameras, that's just gonna keep increasing. And just to be clear, this data includes all the FF files of all meteor detections, all the metadata, basically all the stacks and time lapses. So that's it's quite large. That is the current plan. If someone is willing or knows an institution or something that is maybe willing to hold the tape somewhere, we could probably organize that. Having a couple of backups across the world is always a good idea. And that's the current plan. Just handling this ginormous data volume. Okay, there we go. So Dave is answering here in the chat of how to actually how to access this data. So yeah, thanks, Dave. Okay. Are there any other questions or things that people want to discuss before we take a longer break until then the second session? So yeah, Murray, go ahead.
Oh, just a quick question. I know that all the presentations have been recorded as well. Will the chat also be kept? Because there's a lot of good questions and ideas in that.
Oh, that's great. Yeah, so actually once I stop recording, it saves a text file. And I'm going to share this text file with everyone with the recording. So yes, thank you for asking. If I forget, please email me and I'll upload it. It's going to be saved. Don't worry about it. Okay, so Paul has a question. Paul, go ahead.
Yes, Dennis. Are there plans to improve the current machine learning filter? Because I've been uploading a lot of extra sessions, and I have 26 RMS cameras that I confirm every day. And I see some don't have any false detections, but some do have remarkable, where there are bugs and birds flying. This was not well covered, I think, in the original set.
Yep. Yeah, that's a great question. So just for context, the reason why we have that machine learning filter that's separating bad detections from meteors is because of Paul's and a few other people's extremely hard work where they manually filtered all meteor detections. And in the initial run, when we developed this method, we didn't really have a lot of bugs in the training data. So the current detector, the current filter works really well on airplanes and clouds and all sorts of things, but it does let some bugs through. And Paul is asking when we're going to retrain the model. What we've done is the way that was developed initially is that there was a student in Ireland who did this as his master's project. And he gave us a model that we adapted, incorporated into RMS. And there were a couple of people who were instrumental who led that effort. But I think we should probably try. I think everyone is quite short on time. And if I had more time, I would definitely do it. As I understand, the initial issue is that the way the student trained a model, I think he did it one step at a time instead of it being kind of a one-shot procedure. And the way he didn't really document well how he got to the model. But I think what we can do now is we can take the current model and then we can just kind of retrain it starting with these initial parameters on additional data. It's just we need to find someone to do it and we need to find time. So if someone has a burning wish to do something fun with machine learning and Python, reach out and that's a fun project. There's a lot of data and Paul has been providing a lot of filtered meteors and filtered false positives that can be used for that. So yeah, I can't give you any guarantees myself, Paul, but if we find someone to do it, it's going to happen. Thank you. Okay, any other questions? Well, if not, I think we are somehow right on time. I actually planned this meeting to end now, at least this first session. We had some amazing talks. This video will be put on YouTube. If you gave a talk, you don't want it to be public or on YouTube, please let me know. I'm gonna remove it from the recording. If you want to reach out to any of the speakers, you want to discuss some interesting things with them, there's just either you recorded their email address that was in the slides, or you can reach out to me or to the group, or directly we're going to put you in touch. And yes, that's about it for the first session. Thank you for coming. And I'm going to stop recording now.